Hey everyone, good afternoon, and thank you very much for joining us today with our 2D and 3D visualization with geoscience data in Python. My name is Orhan, and I will go over a lot of introductions today before the actual sessions start. But before everything, I would like to show you this AGU behaviors, which is expected from all of us by the organizers. So like showing compassion, showing inclusivity, and speaking up. And please note the email very down if you need any to report any concerns. As I mentioned, I will be introducing our team and team members and how we are going to cover today's materials, which is a lot. Before everything, I would like to make sure about one thing. How many people in this room are going to follow along with us today's tutorial through their, just follow along through either binder or local laptop configurations? How many people? Okay, I think majority. How many of you folks are going to be using your own local configuration on your laptops instead of binder? Okay, there are reasonable number. And did you get your systems like spun up, or will you need any help with our team members? Any person in the room who will need some help from our team members through I am like introducing my team? Because like simultaneously we can get some of our team members to room and help you guys if you need any help, or if throughout the event, just as you can see here, you can also ask us. And how many of us are going to be trying to use Binder Hub for still interactive visualization, but not through their laptop configurations? Binder, 1, 2, 3. Okay, so I would like to ask you one quick favor, because while I am introducing, which will be taking some 6-7 minutes, we can get the Binder Hub up and running for everyone else in the room. It's going to be taking some time, maybe 7, maybe 10 minutes, depending on the situation. So I would like to show this link on the right tab. So if you have a link to our presentation, which I think I had shared with all of you on Thursday, just find that link, Project Pythia Cookbooks, which is going to be the delivery method today. We will also introduce you what Project Pythia is, but for now, just please click on this Project Pythia if you are planning to use our Binder Hub for following along with us today, the material. And if you are in this Cookbooks gallery page, scroll all the way down, and since our first session is going to be this advanced visualization cookbook, what you are going to do is, again, if you are not going to use your own Conda environment in your local laptop, if you are going to use Binder, click on this launch Binder icon here, just like this. Since I will be using my own laptop, I will close this for myself, but that's it. So it will take some time on your end. If you have a reliable internet connection, it will be probably 7 minutes to 10 minutes while we are introducing ourselves. So I will be turning back to my team, and I would like to introduce. Again, my name is Orhan İroglu. We all are from the U.S. National Science Foundation, National Center for Atmospheric Research, or NSF-NCAR, as we call it. So this is the first acronym today. Hope it's not going to be much, but NSF-NCAR is where we are from. And at NSF-NCAR, so let me first introduce my team members today: Julia, Philip, Scott, and Nihant, and myself, Orhan. We will be in room today, and whatever reason you would like to help from us, just raise your hand. Or if you are on the Zoom call, just raise a question in the question and answer interface that is provided to you. And one of our team members, which as you can see here, is either me or my team member Nihant. So we will be keeping track of the Zoom questions as well, and we will be helping you out as soon as we can. And if you raise your hands in the room, one of our team members will be walking to you and hopefully fixing the issue during the event. If not, so we will have some contact information and we can fix the things afterwards as well. And we will have Stash over the Zoom call. So, and Stash is going to be presenting or maybe answering some questions. Okay, sounds good. And that said, this is also linked to what is provided by AGU about asking your questions. So it's going to be over your web browser or mobile application. That said, let me first introduce you the NSF NCAR, where we provide Earth system scientists and researchers with computer models, climate models, complex software tools, and also supercomputers, and also even research aircraft. And under the NCAR umbrella, NSF NCAR umbrella, we are from the Computational and Information Systems Lab, where we do computer science for Earth system scientists. And another acronym is CISL. We call the Computational and Information Systems Lab as CISL with the acronym. Here is the GeoCAT team, or Geoscience Community Analysis Toolkit team. And you can see me within the team, and Julia as well, and also Philip. And we have a number of other colleagues who are not here today, but we are a team of 6 software developers with diverse backgrounds who are dedicated to developing software tools for data analysis and visualization purposes in geoscientific research fields. And we have a number of Python packages we created and have been maintaining. So those are GeoCAT Computational for data analysis and geoscience data, GeoCAT Visualization, which is for visualization purposes, and Julia is going to be walking you through a lot of functionality from GeoCAT-viz today in the very first parts of this tutorial. And GeoCAT Examples is a plugin gallery in a scientific Python ecosystem, and also GeoCAT Applications, which is going to be coming soon. And we also have another package that's called UXarray. The name maybe is suggesting to some of you guys unstructured XArray. And we will be walking you through UXarray functionality, visualization functionality today with Philip and myself. So hopefully. And there is a feature request form here for everyone else's reference. Again, if the things don't go very smoothly today, that's very understandable. We will have a lot of material today. That's okay. And if you can reach out to us afterwards, anytime, we are more than happy to help you with any situation. And for Wiser team, Nihant, would you like to come over and take it away?
Hi everyone, I'm Nihant, and Wiser is another. It's like the sister team of GeoCAT, and our focus is primarily with visualization services and advanced visualization support. So we usually work with our scientists, both NCAR and external, and help them visualize their data. And in that process, we use a lot of packages and stuff, with the whole goal being using visualizations for communicating to the general public. And another thing that we do, which is very relevant to this session, is Vapor. We develop and maintain a 3D data visualization software called Vapor, and we'll talk about Vapor shortly. And lastly, we also conduct applied research into 2 areas. Like one is data compression, and we are thinking of getting into UX research more in line with the things that we can do with Vapor and how we can expand Vapor in the future. So over here, the other team member who'll be with us is Scott. So Scott will go through Vapor, and the third part, you'll hear a lot about Vapor from Scott. And Stosh is online, and he'll be helping us answer some questions. Moving on to Vapor. So Vapor is a data visualization package that was developed at NCAR. And it's been around for a long time. I think the first version of Vapor was released around 2007. And I know we have many other 3D data visualization packages available, like Wizard and ParaView. But the good thing about Vapor is that we built Vapor as a means to support the geosciences community. So we have some features that allow you to organically import some of the data sets that are most commonly used in the geosciences. And of course, it is open source, community driven, and the focus with Vapor is interactivity. And the other thing is we recently released the Python API for Vapor. So previously we only had a GUI version that we could use to interactively explore data sets, but now we have a Python API where you can go back and forth between the GUI and the Python API, or you can use Python API to, do your analysis. And yeah.
Thank you, Nihant. And Julia, could you please take it away from here for Project Pythia?
Hello. I'm going to give you a quick overview of Project Pythia since that's the infrastructure that we are using today. Oh. Okay, so we're going to go to projectpythia.com.org, which looks like so. So this is an educational learning portal for Python for geoscientists. It is related to the Pangeo community, if anyone here is familiar to that. This is part of the educational efforts that goes into bringing people up to speed. They know what packages to use. They have the know what the Pangeo stack is and can maybe eventually contribute to that stack. So there are a few pillars of our Pythia project. The first that I'd like to share with you is foundations. So this is a textbook that kind of brings you through different packages that we think are foundational to your Python learning. Two I'd like to highlight are we have some matplotlib chapters that are useful if you need a refresher on any of your visualization needs. And CarterPy is another foundational package for geoscientists. We also have a gallery of external resources for learning Python, and today we'll be using cookbooks, which are the step after foundations, more end-to-end workflows that are more specific, more domain specific than something everybody needs to know, but show how the different tools work together. And again, if you haven't already, scroll down and launch the binder for the Advanced Visualization Cookbook, and we'll be using the Unstructured Grid Cookbook as well. And at the end of the session, make sure you shut it down. So thank you.
So yeah, as Julia mentioned, and one additional information here, these cookbooks are really comprehensive. We cannot cover all of them in a half-day event, so I highly recommend you, if you are interested in some of these topics afterwards, please go ahead and check them. There's a lot of information there, especially about some of the Python tools today. And we are putting them together in a way that they could be most beneficial for self-learners through their own reading as well. Turning back to presentations. Okay, so let me walk you through our schedule today. We will have 2 breaks, which are gonna separate 3 different parts. In the first part, we will be covering basic and advanced visualization in Python, which is gonna be covered by Julia. And it's gonna be about 60-ish minutes before a 10-minute break for coffee and tea. And after that first part, we will be covering interactive visualization in Python with a tool stack called HoloViz. Then we will be introducing our unstructured grids tool, UXarray, and those 2 are going to be another 45 minutes before a second 10-minute break. Then the last part of today is going to be 3D data visualization and Vapor tool with Python API, which is going to be another, I think, as far as I can remember, 75 minutes. Then it will involve a 50-minute wrap up and conclusion section at the very end. So I think we can start with the first part by Julia now. But before that, I would like to ask whoever started their binder. So were you successful there? So did you get your binder spun up? Yes. Yeah. Good. Any issues in the room that we would need to help with? Yeah. Maybe in the break. So are you good to survive until break? Okay, sounds good. Okay, so any more questions or yep. As far as I know, that's kind of like up to AGU organizers. I think they don't provide Zoom to the in-room people, but if you ask explicitly, then they might. I'm not sure. We are not in control of that part of the event, unfortunately. So, any more questions? And one more time, question and answers. If you raise your hand, question can be alive here, or you can also type your questions into the Q&A interface provided by AGU. I think we can just start now with Julia's part. We can switch to yours if you're better.
First, I'm going to post the Zoom link in the Q&A. So let me know if that works for you. Farhan, can you stop sharing? Are you sharing? Says I can't share while someone else is sharing.
Says you cannot share your screen because someone else is sharing.
Is the room sharing again? Yeah. But the Zoom participants have to do that, right? Oh, okay, so let me go back to yes. Sorry. Okay. No, it's not working. Yep. Yeah. Thank you. Can you zoom in a little? Oh. Okay. Awesome. Okay. Thank you all. Thank you for your patience. Were you able to see the Zoom link in the Q&A? Do you have access to the Q&A? Mm-hmm. Yep. I added it as an answer to the hello question. So let's begin. Well, when you're beginning learning Python, one of the first challenges you have is not knowing what's available. And then you very quickly have a next challenge, which is there is so much available. How do you sort it out? How do you know what to do? So this, briefly, we're going to begin with an overview of different common plotting packages that might be useful to know. This is not going to be an in-depth tutorial on these packages right now, just maybe a quick glance at what each one is so that you know maybe where to look for in the future. Okay, the first package you're going to learn is matplotlib. This is the workhorse of geoscientific or any visualization in Python. Most other packages are built on top of this, borrow syntax, keyword arguments. A lot of the coding will look familiar between things that are built on top of matplotlib. So first, just a simple example. It doesn't get much simpler than this, right? We import our packages, we plot, and we've done a few minor adjustments here. Next, you have CarterPy. If you've heard about basemap before and are trying to keep those two straight, basemap has been deprecated and CarterPy is now the way to go fully. This is for plotting on top of maps, which I'm sure a lot of people in this room have had to do at some point in their research. So here we're just not going to plot any data, but create a map projection. Here, plate carré, and there's a whole world of different ways to display the world available to you. GeoCAT-viz, which Orhan briefly introduced. This is a series of utility functions that make plotting either a little bit more easy to get things up to publication standards for you, or they offer new utility for geosciences that isn't in Python already. One thing I'd like to take the time to show you is the GeoCAT examples gallery. So here's a whole collection of different things that you can plot in Python and instructions on how to do so. And a lot of these are based on the previous NCL NCAR command language, which was very popular. So just kind of going to scroll through this to maybe have some of these images burn into the back of your mind of things that are available. And some of the examples that we'll do today are more fleshed out versions of things available here. So it keeps going. There's a lot of plots available. So this is a great resource, a tool for you to use. Back to here. Okay. Next is MetPy. So we're going to use MetPy today for making a skew-T plot. MetPy is a collection of tools for mainly weather data, and they're another project within UCAR. They're in the Unidata team. And here's an example of how to make a skew-T plot. We'll talk about this more later, but you create your data and you add the lines that you're interested in, the moist, dry adiabats, etc. And you end up with something that is still running. Oh, it didn't. Oh, there we go. Something like this, which you've probably seen in some atmospheric science class on your way to this room today. Vapor, you'll hear more from the package team behind Vapor later today, but this is for interactive 3D plotting, and there's a Python API, which you'll find useful. Plotly is another choice for interactive plotting. Plotly has functionality in several languages. So here is the Python Plotly documentation link right here, and an example of their functionality. This isn't up to date, so I'm going to quickly launch this and move over to that. Yep. But while that runs, come down. Yeah. Yeah, it is. I'm just gonna keep moving forward while it's working. Okay, Seaborn is another high-level interactive plotting library. This is definitely built on top of Matplotlib and has a lot of earth science-related examples. Could someone?
There's a question.
So here we're going to use Seaborn to make a heat map. Again, go to their documentation to learn more, but you could quickly see that this is much easier than it would have been for you to try and generate a heat map from scratch on your own. Okay. Again, Bokeh, this is JavaScript-powered interactive visualization plotting. There's actually a known issue with their latest version on the cloud, so we don't have an example for them today, but they're very useful going forward. And UXarray you'll also learn more about, which is great for unstructured grids. Lastly, I'd like to show you HVplot. So HVplot sometimes can be confusing to keep all of the different pieces straight. So there's data shader and hollow views, which are wrapped to create HVplot. And all three of these are within HoloViz. So I was trying to, like, what are these four different things? I have to learn about them separately. If you want to get under the hood, you can learn about each piece. But if you just want to use it, HVplot is probably your starting point for using this functionality. Okay, so we'll ignore this JavaScript warning because it seems to work just fine, but you can kind of move around the same plot that you're using and zoom in on different sections, and it's very useful for exploratory data visualization. And I thought this library was useful, or this image was useful from HVplot's documentation. So here are some data libraries that you're likely familiar with or already using. And then you're going to use the HVplot interface, but it's going to be using, without you having to worry about it too much, HoloViz and Data Shader, which they themselves are using Bokeh, Matplotlib, and Plotly. So it all kind of comes together, and maybe HVplot is where you want to start. So that's a brief summary of different plotting packages. Next up, let's talk about what makes good visualization. So we want our figures to be eye-catching. We want them to grab your attention. We want them to be accurate, not misleading. And so there's some pieces that go into that. First up, I want to show you the Datasaurus. So maybe some of you have seen this image before, but here we have 13 different plots of data that have the exact same statistical summary. They have the same means and standard deviations and correlations in all directions. So here's an example of where visualization is really useful for telling the full story, especially when we see lines. Is there some sort of wave function going on here? Are there fronts? Is there a dinosaur on the loose? You can't really tell just from the statistical summary. So data visualization is important. Okay, so we're going to talk about how to make, oh, I forgot to import my packages. Step one, import everything. Okay. Here's just a simple line plot, and we're going to show just briefly some customizations you can make. So maybe this isn't exactly what you want yours to look like, but think about making your title a large enough font for people to read. Maybe your labels are bigger, but not quite as big as your title, and just know what customization keywords are out there for you, and maybe try to be consistent across different plots that are within the same publication. One thing that can help you with that is the Matplotlib parameters. So if you list all of the keys that are available to you, you can set these to change their default value that look good? Okay. Just want to make sure everyone can see the font while I'm talking about making your font large enough. There are so many options here. You could make all of your titles appear in Comic Sans if you wanted to. You could make sure everything is spaced large enough that you tick marks instead of setting this every time you call a plot. Yeah, I just zoomed in a little bit, so I'm gonna zoom in more, but then it looks fine up there, right? On my screen, it feels like the nav bar is eating the page. Yeah, okay.
Do we need the folder open with all the directives?
You're right, we can close that.
That should be a little bit.
Exactly what I wanted. Okay, let me go back to the top. You are going to call matplotlib parameter keys. An app? Maybe. Here, I can post this in the Q&A. I think someone can. Okay. So it's a long list. Okay. And again, all of this is available on the cookbook pages, which is an asynchronous resource that may grow after your time here today, but isn't going to go away. So you can refer to that for some of these arguments. Okay, so how you would change one of these permanently is with matplotlib.rc params as a dictionary, point to the key that you want to change and then set it. This, we are not setting it right now on the cookbook, but this is just a code block, not actual a code cell. Okay. So GeoCAT-viz is also helpful. So some utility functions in GeoCAT-viz abstract out the tons of lines of code needed to set every single thing by having our own kind of default values for your titles and labels, etc. So this is just a simple call to GeoCAT-viz with set titles and labels. Lots of functionality in there in GeoCAT-viz that'll be sprinkled throughout the day. And I couldn't give you a talk on good visualization without getting on my anti-rainbow color map soapbox. So it's important to think about your color maps being sequentially oriented, like if that's what you're trying to show. So, so when you print things in grayscale, or there's people who have color blindness, you want things to still appear the way you want. And you can kind of look down here and see if you used a rainbow color map, your eyes are going to be drawn to these bright spots, and what's yellow and blue might look the same to you. And so it's not going to be super useful. Okay, and there's also ways that you can make your data misleading by adjusting your y-axis, or you can highlight the differences you're trying to portray. So here's just a brief summary of different ways that your differences can be highlighted or not. But I've already used more time than I planned, so I'm going to move forward to Taylor diagrams here. Okay. These are a way of visually representing a statistical summary of data. So I know we just talked about the statistical summary not being the full picture, but you might want to show a statistical summary of multiple different things together. So a simple Taylor diagram, you're going to create it with the GeoCAT-viz Taylor diagram class and call this add model set. And here we just put some simple data on 1 point. With being so zoomed in, it looks too small. Let me change the font size. Make this a little smaller. Okay. So how to read a Taylor diagram is your distance from the origin represents your normalized standard deviation. So you'll have a reference data set that everything is compared to. So you're dividing your data standard deviation by your reference standard deviation. And then your angle from the horizontal axis is going to be your correlation coefficient between those two data sets. So to kind of bring this home, we're going to do this again with ERA 5 data as our reference and CMIP for our model. And we're going to look at temperature data that has had some pre-processing already done. It's been spatially averaged and subsetted in time, but we still have to do just a little bit that I'll kind of lightning move through. We have to get our data, we have to resample it in time, and then we have to just grab the temperature data. For the model, what we're going to have to do is change our time indexing, so it's not in a object class, but a date time class. And you need to get your standard deviation, again, dividing to normalize it. And we can use UXarray's built-in standard deviation and correlation coefficient functions. And then when you plot all of these, what's mainly going to be different here is the add model set. We've specified some more keywords. And we've also added a model name, which is going to create a legend in the lower left of the different data points and what they map to. Okay, again, let me make this a little smaller so we can see it. Okay, so we were looking at the RCP 85, so that's business as usual if there's not any like huge efforts to mitigate greenhouse gases. And our model set is fairly close to what has been happening based on the standard deviation being near 1 and the correlation coefficient being near 1. You can also plot multiple models. In this example, the only thing that's really different is we're going to add in some root mean squared contour plots. So that'll be right here with the Taylor add contours. And this will add lines of constant RMS data, RMS values. And so you can see those with these concentric circles. Okay, and you can also plot multiple variables. We're running low on time, so we're just going to run through it quickly, but you just want to make sure your keyword arguments are different, and you can add a legend to show the difference in the two. And you can add a third layer, which is by plotting bias with triangle errors. So, and to do this, you need to make sure you turn off any keyword arguments that are specifying how you want your plots to be drawn, because now how they're drawn is determined by this bias array, which you need to pass in. And you can add a bias legend, which is going to appear here. And that's your fast overview of Taylor diagrams. So hopefully if you were familiar with those and you wanted them in your plots, it's a little easier. But if not, maybe you'll find a use for them. Okay, we have 3 more plot types to fit into 20 minutes. So skew T diagrams, I already showed this a little bit. What's going to be on here is your temperature and pressure lines, dry and moist adiabats, and your mixing ratio lines. So where you have constant mass of water vapor to dry air. Okay. And we've already showed a basic example of this. So we're going to get our sounding data, get our interested variables, and make another basic skew T plot like the one we saw at the beginning. Okay, so what is, I think we already kind of looked at this a bit, but one thing that's interesting here is we are subsetting our wind barbs, our U and V values, just so that they don't go too far up from where we subset from the Y limits of the skew T diagram. And when you want to add your moist, dry, and mixing ratio lines, you just do plot underscore and then the line that you're interested in. like so. And you can see all these beautiful areas now highlighted. And in this polishing the plot section, we show a few different things you can do. So one that I like is we are going to subset the wind barbs so that we see fewer of them and they look less visually messy. You can also change the rotation. So when you don't have it specified, it's going to default to 30-degree rotation, and before we had it at 45. And as always, titles and labels. Titles and labels are great. And it looks a lot cleaner, even if it is very big on the screen. Okay. In this last cell, we're going to show 4 different SKU-T plots at once so that we can move through them quicker. So we have an example of, it's still running, getting our lifted condensation levels, how to highlight where that is, how to add a line of constant temperature if that's what you want to highlight. Showing CAPE and SIN, so your convective available potential energy versus your convective inhibition, which is relevant to determining how likely a thunderstorm is going to be, like how much advection is available to it. And a hodograph, which shows the different wind barbs as you move up, which is important for understanding wind shear. So use this as a reference for the different types of SKU-T plots you might want to show. Now, spaghetti plots are essentially just a lot of line plots on the same figure. They can show movement or the chaos inherent in a system. We're going to use them today to show both a hurricane plot and lines of constant geopotential or geopotential height. So first thing, just import all of your packages. And spaghetti plots can be used for hurricanes because as meteorologists or climate scientists, you might be familiar with different ways of portraying a hurricane's potential path. And some of these ways are very alarming or confusing to people who haven't been trained. Like the cones of potential, like probability where the hurricane can go, just looks like it's growing way more than it probably is going to grow. So one way to display this differently is with spaghetti plots. So we're going to use some global ensemble forecast system values from Hurricane Sandy, and we're going to get them with tropical. So just read in your data, use this get storm to UXarray, and then you'll see that we have a lot of different forecasts available to us. And we're just going to grab the AP01 forecast, not for any special reason, but because we needed one for an example here. Okay. And that the different keys in this dictionary are the time of and the day at which the forecast was initialized. So first, to take a look at it, we'll do a spaghetti plot of one feature. So here in this code cell, we're just generating our Carter Pi figure to make sure we have that down. So again, you set your projection, you can add features, grid lines, and we are making it so that our lat and long is not repeated on top and bottom. And then we're going to go in, and for that one ensemble member, we are going to plot every forecast that it contains in a for loop. And they're set to be the same color right now. And then we'll go ahead and plot the actual path of the hurricane. Okay, and what do we see? It's great that we were able to make this plot, but it could be misleading. These forecasts are taken at different point in time. And so here it looks like they all have equal weight, equal importance, and equal likelihood, when in reality, they're not all made equal. Our more recent forecasts are going to be more likely to happen. So we are going to add some color mapping, and there's some manipulation of the color bar that might be useful for your future projects, even if they're not hurricanes. So what's going to mostly be different here is we're going to use date time to get date information from our file names or from our keys within our ensemble, and we're going to normalize them and pass that normalization into a color map. And then we loop through the color map, changing which discrete color through the map each line is plotted as. And the last difference is that you need to add your color bar. And so you're going to have to point to scalar mappable of the color map that you created. And so what that's going to look like is things getting more red, and you can see that the later forecasts almost blend in with what actually happened. And this is expected. Similarly, we might want to plot all ensemble members, but from a single point in time. So here we're going to run from AP 0 to 20, and we're also going to use a for loop. And in this time, we're plotting them all as blue because they are of equal weight. Okay. And so now you can see that most of the forecasts by 2 days before Sandy hit had a similar interpolation, similar idea of what was going to happen, except this one ensemble member that I don't know exactly what was going on there. Maybe they thought the storm was going a lot faster than it ended up going, or just took a hard right. And then let's look at a contour plot quickly. So we are going to show you how to plot contour plot on the North Polar stereographic projection. So this is going to be useful also not necessarily as a spaghetti plot tutorial, but for a Carter Pi lesson. So in this cell, we're setting our projection to North Polar stereo, and we've set the labels to false because we are going to custom set them ourselves to be something we like. Okay. But first, we are going through this data and just plotting the same constant pressure level in a for loop. And one thing you need to do is add cyclic longitudes so that we can deal with any artifacts where your data wraps around from 0 to 360 and it's like the same data point again. You don't want anything kind of funky happening there. Okay. Okay. And so we get kind of this is this lovely spaghetti plot. And then to add labels, we have some logic going on here because we want different things to happen when we're at the north and south or anywhere else. So we have a couple if statements to find where we are, and then we just set our axis.ticks and specify how we want them to be. And that's how you get these nice every 30 degrees. Zoom it through. So if you wanted to add color bar manipulation to this plot as well, even though I can tell you there's not a temporal pattern as we go through, what we're going to do is similarly, okay, this is where the fresh code starts. We are going to get the color map we're interested in, and when you add this n parameter, it's going to make it discrete to grab the number of contours we're doing, which is 19. You can get the bounds for this with NumPy line space. And then you are going to call the index of the bounds of the color map that you're hoping to use. And then your color bar itself has some more stuff going on. You're going to pass in, again, scalar mappable of your color map. And then here we're showing you how to manipulate your tick locations and labels so that your ticks are in the middle of each boundary, even though, so it's displayed in a way that's more readable. Like so. So now you can actually tell what colors. Oh, so if you're just trying to save, go to settings and turn off autosave documents. And the last piece of this that I might show you is, say we know our system is chaotic, but we still want it to be colorful and eye-catching. We're going to just pick random colors, but we're going to pick them ourselves. So you would do that simply with this color list, and you iterate through the color list. And this is going to be much simpler than the other methods. And then you don't have to have a color bar here because there isn't a color bar. And the last plot I'll show you before I hand it off to Orhan is how to make animation. So in Matplotlib, there's two different main ways to make animation that we'll show you. So one is artist animation. This one might be, say you wanted to make a bunch of images and then you took them, combined them together, and then moved through those frames and made an image. Artist animation helps you with that. Whereas functional, you create your image object and you are editing what that image object is in time. So there's a couple different things to look out for when you're doing this. We're going to use a pretty simple example using satellite data from GOES. Okay. So first we'll do artist animation. And for this to work, you might have to set your Matplotlib RC parameters, which we talked about in the very beginning of how you could change your font size. But here we're using it to make our animation run using JavaScript with JS.html. And so this will help it run if you are on the cloud or any service like that. If you're running locally, you don't need to do this. Okay, so we'll grab our data and create a figure. Okay, and so this figure, we've created the figure, even though it just looks like white space to us. There's an object there that Python knows and is seeing. So we set our dots per inch, and then in this fig size, this is a useful tool here for making your figure size match your image size. It's basically just removing any white space surrounding the image and just makes it a little cleaner. This will become obvious when we make our image look like something. So here we are using list indexing in Python to make a list of lists of artist objects that are basically just from opening each image file. And then we pass that list into animation.artistAnimation. And then you can call up your animation and it should look really pretty, and I'll give it 3 seconds. Yeah. Is this one still running? Okay. So things you're going to specify are your intervals, whether or not you want it to pause a little bit before you move on. And the hard part of this is probably getting your data visualizations up to the point that you're ready to iteratively create the list that you animate on. And then if you wanted to save the animation for later, you just call .save on your animation object. Function animation is going to look pretty similar with a key difference that I'll point out in a bit. So we're going to open our surface temperature that we'll use here. Create our CartaPy object. And then we're going to create an initial frame. So here we're looking at the first time series. We're going to plot that, make sure it looks how you want with, you could do a plot show there. And we need to create an animation function that will then update the figure as we move forward. What is important here is that we set color bar to false, which may be surprising to you, but since we're changing the same image, if we have a color bar, we change the image every time, what's going to end up happening is like this. So it's visually recursive, I guess. So you set that to false. And then you create your animation.func animation call. Oh, did I forget to run something? Yep. So this call looks pretty much the same as your artist animation call, but what you're passing into it is a little different, and you're passing in your animation function that you defined yourself instead of passing in a list of artist images and then displaying it. Okay, which will again take a second. So we can just watch this for a little bit to really hone in that you want to turn that off. Okay, and here you go. This is the surface temperature changing through time in this animation example. So animation can be really intimidating, but these calls to animation were actually really quick and maybe one of the simpler examples we went through today. Because I think the hard part is getting your figure exactly how you want it for that first time step and then adding in the temporal animation component of it. So thank you for that whirlwind tour of some of the advanced visualizations available to you. Next, I'll pass it back to Orhan.
Thank you very much, Julia. So even though we took some time of yours and the technical difficulties as well, it was great. So actually we will have a break in about, 10 minutes. I think we can start with the next part. Let's see, let me first take this type of these. So let's revisit our slides for reference. What we had done until now was these basics and advanced visualization topics in Python for geoscience data visualization purposes. Before the break, we still have around 10 minutes, and in that part, we will have been covering the interactive and high performance visualization, and we will be doing this. This is going to be after the break. So for this one, I think we can get started and see. Maybe we can at least make an introduction, because this is in the same cookbook as part of it as well. So as Julia mentioned, Matplotlib is the Python workhorse for general purpose or geoscience data visualization, right? But when it comes to interactive visualization, so how many people in the room are, rather than, or maybe in addition to static plotting with Matplotlib, how many people in this room are using some kind of interactivity within their visualization efforts? Which like packages? Is that in Python? Which one? Okay, all of you. Great, thank you. Anyone else for interactive visualization? Okay, maybe we can extend the introduction part better for better understanding. So and maybe another information here, even though we put these into interactive visualization and unstructured grid visualization sections into the same part, there is no direct relation between them or prerequisition between them. So interactive visualization is one thing you can do for any general purpose or geoscientific purpose visualization in Python with the help of a number of packages. But in unstructured grids, we will be using some of them, but it's going to be a new domain, a new field we will be exploring today. So regarding the interactive visualization, as I mentioned, I will still be using the same cookbook. Let me first find it in my tabs. I think I can start this again. And whenever I am not showing you any code, I would like to stick to the rendered notebook and Cook notebook in the PTIA website because it has a better graphical user interface for some of those warnings and admonitions that I would like to show you as well. So let me open this HoloViz visualization notebook in the very end of this advanced visualization cookbook in PTIA.
Click the arrow on the top left so it gets rid of all of the categories.
Which one?
On
This
the-
one?
Yeah.
Oh, okay.
That
Yeah,
should make
thank
it
you very
easier to
much.
see.
Okay, should be better. Yeah, thank you. So what is interactivity? Actually, interactivity can cover a lot of different things, right? So, but in this context today, as part of our tutorial, we will be covering interactivity of plots with panning, zooming, and while doing these, getting some dynamic plots or non-dynamic plots, which means as you zoom into the data fidelity gets increasing and increasing so that you can see the further details of data with your zooming into visualization. And it's the dynamic plots. And what's going to be also covered here is, let me remember. So the HoloViz tool stack. So HoloViz as VIZ is a tool stack which covers a number of Python packages that are making us able to do interactive visualization with even really large data sets in Python. And today we will not gonna be covering the big data part of it, but whatever we are doing today can be applicable to really high resolution data sets as well. But let's get started. And another thing here is, which I have been experiencing in this ecosystem, is HoloViz and the individual package. One of the packages, HoloViews, are generally confused with each other. HoloViz is the name of the tool stack or the group behind all of these packages, while HoloViz tool stack has a number of packages which are called HoloViews, GeoViews, Data Shader, and maybe others. And in this interactive visualization notebook, we are using unstructured grid, one of the unstructured grid formats, which is called MPAS of NCARS, NSF NCARS, but it is not directly related to unstructured grids. Whatever you see today as part of the interactive visualization can be applied to any structured data as well, structured grids data as well. So this is the attention to the audience for that purpose. If the actual focus here is unstructured grids visualization, we have a dedicated cookbook for that one, which we'll be covering after the break. So you see, we have still 7 minutes, and I think we can get started with this one. Again, how to use HoloViz tool stacks is one of the biggest focuses of this first section of the second part. And for that, I think prerequisites can be HoloViews, the package, and GeoViews for some cartographic projections as well. As you can see here, we have a number of package imports to get HoloViz tools to provide us some interactive visualizations. One of them is the HoloViews, as I mentioned before. And another thing could be OPTS, like options system of the HoloViews, to customize your plots in the HoloViews. And another thing here can be Data Shader, which is basically a really high speed and high level rasterization package of the HoloViz tool stack. And we will be using that one for some rasterized plot generation purposes. And all the other things are generally, for example, UXarray and other things are for general purpose data ingestion and pre-processing purposes. Cartopy here is going to be used for projection purposes. And I think that's it about the HoloViz. So as I mentioned before, we will be using MPAS unstructured grids, which I will not go into the details for today because the actual focus here is interactive visualization. Because of that, there is a number of pre-processing utility functions here, which is basically for getting the unstructured MPass data ready to be visualized with a HoloView package. And that includes making use of some connectivity information and other conversions and kind of the repair and treatment of the data to be able to be plotted with the HoloViews package. So as part of this tutorial, we can just skip these utility functions. Loading the data section is nothing more than reading a number of variables of interest from those MPass data sets. And we will be using some 2D face and node geometries from the MPass data. But when we start plotting, hopefully it's going to be better understood what I am talking about, all of those geometric elements. Let's see. By the way, I would like to not skip these parts in my actual notebook in my local Jupyter cluster. So let me just start implementing these as well. I'm just executing these one by one, all of the utility functions. And I'm coming through all the way down to loading data and coordinates. And maybe I can give you some details about these data sets we are using here. So it is a 30-kilometer resolution MPass data. Within the same data set, we have even 3.75 kilometer data, which has several tens of millions of data nodes and faces in it, which is the kilometer resolution data, kilometer scale resolution data, which scientists can use for example, individual storm resolving purposes. So in this interactive visualization part, we will be using the 30 kilometer of it, but in our local tests and local development, we have been using the 3-kilometer data as well. And all of these tools I'm going to be introducing today are able to run and reasonably generate plots with such a fine resolution data as well. So I think I had implemented this one, but once again, okay, we talk about mesh. So in this cell, what we are getting is we are getting our MPass data read in, then we are generating triangles out of those data nodes in the unstructured grids, which I will be in detail introducing to you in the next section, which is going to be unstructured grids visualization. But basically, we are generating triangles out of the data nodes, and those triangles are being rendered with the help of one of the HoloViews tool here. So the first thing here is getting the data, converting it to what is called is like triangular mesh, which is a consumable data structure by the HoloViews package. And in the next section, we will be visualizing that triangular mesh with the HoloViews. Let me execute this cell 2. And the dual mesh, it is kind of like MPass specifics. So I wouldn't like to go into that detail as part of this interactive visualization because I would like to really emphasize the interactivity with these things. One last minute, which I would like to find a good way to stop as well. I think I would like to stop at this point. So I would like to turn back to my cookbook again and show you this note here. This one. If you are using HoloViews, the very first thing is HoloViews is a package which can also support Matplotlib as a backend. But if you are interested in interactive visualization, you should be choosing the bokeh as your backend instead of Matplotlib. So with bokeh, you can do it. There is a third backend option, Plotly, but I never like personally tried it. I don't know if Philip or someone else tried. I don't know if there is any interactive visualization availability with Plotly, but if you choose Bokeh as your backend engine, just like I do here, you should be good to create some interactive visualizations. So after the break, we will bring the things forward from here. So thank you so much and see you all after the break. Maybe in the meantime, while you are in break, you would like to do this. I am turning back to the cookbooks page again. In the second part of this tutorial, right after we wrap up with the interactive visualization, we will be starting to this unstructured grids visualization cookbook, which will require you to spin up another Binder Hub instance. So you may want to create that one from now. So you should be just good to go in the next section. So thank you so much and see you all in, let's see, I think 10 minutes. Yep. See you all in about 10 minutes. Okay, I think we can start again. It's 3:20. Where we stopped just before the break was this HoloViews extension discussion. So there are backend options like Bokeh, Matplotlib, and Plotly. I have used Matplotlib and Bokeh. Matplotlib is just what is supported by HoloViews package and HoloViz tool stack. So you can just use Matplotlib functions within the higher level HoloViews commands, or you can use Bokeh for, especially for interactive visualization, but there are some other use cases as well. I will execute this. And there are a few plotting and option keyword arguments that I had defined here, which were, this is for rasterization purposes. What is basically meaning is I will be shading between node points. So I would like to use the mean average of those node point values so that I can shade the face in between those nodes. This is the aggregator, what it means. And ProCompute is something for HoloViews package, which makes the plotting much more efficient than PreCompute falls. For options, these are to show color bar always and to choose my color map for cool warm. This is important. So whenever you generate an HoloViews plot, you have a HoloViews object, and through that object, you can customize your plots very flexibly. So you can feed these options call with a lot of different things, ranging from the figure size through a lot of different color bar, color map related arguments. You can have a lot of different customizations of your original plot. So this is the OPTS options system with HoloViews. And I think we can start to showcase some interactivity that would come with Bokeh backend HoloViews plots. So this is a default HoloViews plot, which comes with these simple interactivity features in the right-hand side. So this is the pan, as I told you before, and this is the different zooming features. For example, this is the rectangle zoom to whatever region you would like to zoom into. You can just draw a rectangle and do it. And if you would like to turn back to the original version of the plot, you can just do this refresh. And you have some scroll zooming options as well. You can do with your mouse. And you can also have some save features here. So this is the default interactivity that would come with any HoloViews plot. And there is one more thing which you could do is the hover. So if you would like to see the actual data values while you are hovering over the plot, you would like to put this into your input as well for the HoloViews plot. So as you can see here, we are generating a rasterized HoloViews plot here with the default plot keyword arguments I showed you before. And we are using our triangular mesh data to rasterize. And then we are customizing our rasterized plot with a lot of different options, keyword arguments. So in this case, I am feeding my plot with a hover tool, which gives me nothing more than this, but don't worry about the data visualization here, because just for showcasing purposes, I am using the triangular mesh that is generated from dual one. The first one was the triangular mesh that was created from primal data. These are just two different data sets, you can assume. So that's the difference between these two plots. But what I would like to show you is, I'm not clicking to anything here, but just I keep hovering over the data, and I can see the actual data values over my global points. If I did this here, I wouldn't see any data values because I didn't have this hover tool enabled. There are other tools as well, which I have some notes about, but I wouldn't like to show them. The hover was one of the emphasis here. Dynamic plotting with HoloViews tools is really, really important. So I would like to show you one use case with that one. Actually, there is kind of a reverse relation between the title here and the plotting feature I am showing you. But what I am saying here is, let me switch back to the notebook, rendered notebook, and you will see a good warning there. So dynamic plot. This warning is very important because if you are looking at the dynamic plots through your local Jupyter instance or binder, which means you are actively rendering your data or plot, you can see the dynamic plot features. But if you are looking into some pre-rendered Jupyter notebooks, just like I am showing you right now, you cannot see those results of the dynamic plotting. I would like to showcase these two to you with the difference. And as I also mentioned somewhere here, if you don't explicitly define dynamic optional argument, it already comes with the default value of true. So if you don't explicitly call it to be false, it's already true, which means the previous two plots were already dynamic. And what I would like to show you is, just pay attention to this one. When I zoom into a really small area, it will dynamically render the plot just after maybe a second or maybe two. First rasterized, and it will show you.
Still on the...
Oh, okay. So I just missed the detail I was trying to teach you here. So this is the rendered notebook where you cannot see the results of the dynamic plotting. If you turn back to your Jupyter cluster, again, regardless of if it is your local cluster or the binder, where you are actively plotting your data. So I'm turning back to one of these. Thank you, Philip. Yeah. So just pay attention now. It dynamically renders again and again, and it gives you really increased data fidelity. For example, let me do it one more time. Yeah, but if you do this in the non-dynamic plot where you explicitly say, no, I don't want any dynamic plot, which can also be beneficial for some cases. For example, if you are doing some point rasterization for your data in the global resolution, that would look great. But if you look into some regions of interest, point rasterization couldn't work really great because, you know, the sparsity in your data could make the things really worse in the zoomed in versions. In that case, for example, you may not want to do dynamic plotting, but in this case, you have a really good resolution data globally. So, and as you keep zooming into your data, you may want to get increased data fidelity here. So this one with the dynamic false, let me first execute this and then show that to you again. Even if I zoom into data, it will not re-render here. So you can see whatever was originally plotted. Maybe one more time. Yeah, so you can see all of these ragged views. So that's the difference between dynamic false or dynamic true. And one more time, if you are looking into a rendered Jupyter notebook, just like I did confuse myself about, you cannot see any results of the dynamic plotting. So for example, this is a dynamic plot, but if you keep zooming into, it will not re-render the plot because of it's being re-rendered. So I think that is good now. That is the dynamic plotting feature with HoloViews package. I'm turning back to my local Jupyter cluster to Jupyter instance to look into our plots again. This was the false dynamic. And since I don't know if people are going to be looking into this notebook from the rendered or active instances, I just wanted to showcase the difference here, just next to each other. There are some further interactivity considerations here with HoloViz stack, which are really good examples, but as part of this tutorial, we didn't want to put them because the cookbook was getting bigger and bigger. So you can also afterwards look into them. So in summary, probably every one of us is actively using Matplotlib for visualization purposes, but there is such a toolkit as well. If you are interested in interactive visualization, then HoloViz technologies could be really helpful for you. And when it comes to big data visualization, it's also further beneficial. So with large data visualization in their mind as a priority. In the second part of this, second section of this second part, which I would like to show you again from here, we will be introducing the unstructured grid visualization. And in this one, we will be using our NSF NCAR housed UXarray Python package. So before that one, I would like to ask the room, how many people are familiar with unstructured grids? Thank you, Ian. We have our last summer intern in the room, which who worked on unstructured grids visualization. And I would like to admit there are great features and functionalities here, which were originated by or worked on by Ian. So Ian, thanks so much for that one. So anyone else on unstructured grids? One in the back, okay. So let's make some good introduction there because I think we will benefit from that. So let me switch to my, get rid of these two tabs and then switch to my unstructured grids visualization cookbook. If there is anyone in the room who was not in the first part, you can start this cookbook from here. PTR cookbooks, all the way down, the unstructured grid visualization cookbook. And you will need to spin up a different binder for that cookbook here. After that introduction. So unstructured grids. Let me start with this overview. When it is structured grids, for example, I think the most easy example there is the regular latitude, longitude grids, right? So when it is structured, it's easy to understand, work within a lot of easy workflows. And for several decades, we have been using structured grids already. So there is not much to explore there. And one caveat with structured grids can be counted here. They are not flexible or has the potential to refine the resolution for some region of interest and some really fine resolution data. So what unstructured grids can do is, in addition to, they can enable to define data in any arbitrary shapes because they are unstructured, because they are based on some geometric elements like node points and 2D faces. They can also refine the resolution for some regions of interest in the globe. So if you don't want to define data points or data values in, for example, over the lands, okay, you can do that. You can just define ocean unstructured grids and you can just skip the land, or vice versa. So refining the resolution for some regions of interest, which also can make us to achieve fine resolution data sets. I think unstructured grids is really important to explore. And what was motivating UXarray or the NSF-NCAR like groups, like our Project Ryujin group, to come up with a package called UXarray was that there was no commonly used Python package in the past for unstructured grids, even though there was this was much needed for unstructured grids research. So that was a number of motivations behind why unstructured grids should be important. I would like to show really toy cases to make you aware of what could be the difference between a structured grid and an easy unstructured grid. So let me see if they are, okay, they are generated here. We don't need to play with the Jupyter for that one. So in this one, you can see in the code, I don't want to detail very much the code because it is really like basic structured grid code here. But what we are doing is we are just creating latitudes and longitudes in linearly spaced data. And then we just create a mesh grid out of those two, which means we just create our latitudes and longitudes in some uniform distances. And when we plot them, and we are also generating a random data value here, just for the sake of putting together a structured grid. As you can see here, there is no meaning of this data for sure. Everything is random here, but you can see the well-ordered structures of latitudes and longitudes. So again, this is everywhere. So we can do this with Matplotlib and HoloViz tools or many other tools as well. So this is easy to both comprehend and also visualize, and also perform data analysis functions as well, which is not the scope of today's tutorial. But when it comes to unstructured grids, you can theoretically create any number of data points over the globe with any arbitrary shapes that they could create as faces or cells. So let me just walk you through the unstructured grid toy data here, which is another randomly created data. But what you can see here is we can have, so let me just show this to you. So however many data points we have on the globe, we should have the exact same number of latitudes and longitudes because we are keeping track of those individual points separately, as you can see in this creation. And then we have the same dimensionality data value array as well, data array as well. And we are creating, just for the sake of making, putting together an example, we are creating some triangular meshes out of them, just like you all saw in the previous interactive visualization section. What we are trying to do here is, let me first show you the demonstration, then hopefully the understanding will be better here. Over the globe, you can have arbitrarily defined data nodes, and within 3 of each of those data nodes, you can create triangular shapes, right? So you can assume in this specific unstructured grid format, your grid is consisting of triangular shapes only. So if we call these individual shapes as faces or cells, your faces or cells are consisting always of 3 points in this unstructured grid. But what is really valuable to discuss is there are different unstructured grid formats. In each of them, you can define technically any arbitrary shape. It could be quadrilaterals, it could be triangles, it could be hexagons, it could be other different data formats or polygons as well, so that whatever your use case is, based on that, you can be creating unstructured grids. For sure, there are a number of unstructured grid formats already defined by people from NSF, NCAR, and other communities all around the world. But this is a basic information about how an unstructured grid, if it's visualized, would look like. So you have your node points, and between those node points, you have your faces or cells. Some people tend to call them, instead of nodes and faces, vertices and cells as well. And even though we are covering unstructured grids today for geoscientific purposes, there are use cases to these grids in different areas as well. And another thing, please don't forget about these colorings. I mean, the color values themselves are not important, but we are going to be covering why we should be visualizing on how we could be visualizing unstructured grids, depending on if our data is mapped to nodes or mapped to faces or mapped to even edges in the next sections of this part. So I think such an introduction was needed. Then I think we can talk about why UXarray could be a go-to package in the scientific Python ecosystem, because we are inheriting from XArray. So if you are familiar with XArray on structured grid research, then it should be really straightforward to understand what data structures in the UXarray are meaning and how you could use them for visualization purposes. That's one significant pro with UXarray. Another thing, as I mentioned at some point of this introduction, there are many number of unstructured grid formats all around the world. So what UXarray does is we are supporting already, I think, 4 or 5 of them, and we represent them in a unified UGrid convention-like structure. UGrid is kind of a consensus about the understanding of unstructured grids. It is not an implementation way, but it is kind of the conceptual consensus around, okay, if anyone is going to be defining unstructured grids, these are the required things, required fields that they should define, kind of consensus. So what UXarray does is whatever data format or structured unstructured grid format we support, we represent them in a unified single format, so that whatever functionality we define for visualization purposes as part of this tutorial, you can apply those functions into different data formats or grid formats. That's another, I think, big strength with UXarray. And you can see in the very bottom of this page, currently we support UGrid, MPass, script, and Exodus formats in unstructured grids. And the architecture of the tool is open to plugin-like extensions to support other formats as well. That's it. I think we can move on to the next thing, which is data structures. Again, how many people in this room are familiar with XArray? The regular structured grids XArray. Okay, there are a bunch of people. So if you are familiar with XArray, as I mentioned before, it should be easy to understand what UXarray data structures are for. For example, we have, before this grid data structure, let me first introduce you to the UX dataset and UX data array structures. They are just like their counterparts in the XArray dataset and data array, and they actually inherit from XArray dataset and data array. So what is the difference between XArrays and these? Is the grid information. So in our UXarray, our dataset and data array are aware of the grid geometry because they need to know what is the unstructured grid geometry underneath so that they can apply functionality or they can define attributes. So our dataset and data array inherit from XArray, but they are aware of what is going under the hood for grid topology. So for that grid information, we have a grid object, as you can see here. And grid object, I think I can show you really quick an example here. So again, for those people who are familiar with XArray, you know the open dataset function, right? So you can open dataset, any dataset file with XArray. When it comes to unstructured grids, most of the time use cases are based on you have a grid definition file and you have one or multiple data files, because you have to know about your grid definition, grid geometry, which is most of the time a separate file. Sometimes they just end up being the same file as well, but most of the time those are separate files. So what you can do anytime with unstructured grids is you can explore the grid geometry itself, or you can read a data variable that is defined on unstructured grid format. So with the help of this open grid, which is very similar to open dataset, you can open just a single grid file to explore the geometry. For example, in this example, it looks like we have almost 4,000 node points and almost 2,000 faces, which means faces defined between those nodes. And you can see number of maximum face nodes, which means we have polygons, which can be triangles, quadrilaterals, or up to hexagons in this data set, because the maximum number of nodes per face is 6 in this data set, and so on and so forth. So there are a lot of different data variables as well. I would like to talk about connectivity information, which is very important in unstructured grid research. So we were looking into those triangles and nodes. So the connectivity information basically means each of your faces knows what nodes are belonging to them, so that it can be utilized in data analysis operators, or in this context today, visualization purposes too. Moving forwards, I would like to show you how a dataset and data array could work, just like their XArray counterparts. So as you can see here, we have the same open dataset function, but in this case, it can take two different, or one file here for grid definition and one or multiple files here for data variables. So you can have, again, one file here and multiple files here for dataset opening purposes. After you open any UXarray dataset, your dataset knows what grid geometry they are belonging to, so that you can visualize them. So how they can know that grid geometry is through a UX grid object. I cannot remember where it was. Okay, here it is. So any dataset or data array in the unstructured grids, like UXarray, knows what their grid topology object is, just like here. I think we can move on to data mapping discussion now. So data mapping means we have nodes and we have faces defined between those nodes, and we have data variables of interest, right? So those data variables in the unstructured grids field can be either mapped to nodes. Let me just, so this is a sample mesh. If we have our data values mapped to face centers, you can see them like this. So if you have a data array, you could have your data values defined to the center of each faces, and they would look like this. And how could you understand that is the dimensionality of the data array. So if the dimensionality of your data array is the same as your number of your faces, then those are face centers. Or if you have your data values defined on node points, then you can see them looking like this. And depending on what data mapping in your unstructured grids is, you can visualize them that way. So you can shade your faces, maybe depending on the node values, or you can shade your faces depending on your face values. And there is one more data mapping option here, which is the edge-centered data mapping. In this case, which is not usual, so or which is not as common as face-centered or node-centered data. But in this case, you have your data values defined for each of your edges. So and as we mentioned here, depending on the dimensionality of your data array, if it is the number of faces, then you can see, okay, my data is face-centered or vice versa. After this one, so if you were going to cover plotting values.
If you can cover plotting, I'll do the rest.
So so far we talked about unstructured grids and UXarray, and now we will spinning up to how visualization can be made with UXarray on unstructured grids. For that one, you can remember the previous section tools, which are HoloViz. So we are using HoloViz tools under the hood. We are wrapping them for unstructured grid visualization purposes. But what we are doing here is, since we are pre-processing the unstructured grid data, then the rest of the visualization itself is just really convenient for the user. Our user has getting to convenience with just using UXarray to open their data set and then getting their data visualized without concerning themselves much about how to pre-process data to get them ready for visualization. You can probably remember all of those utility functions from the previous section. So you have to do that for every single data format if you are trying to do visualization for unstructured grids with your own library of interest. But if using UXarray, then it should be taken care of under the hood. So let me quick start to the plotting libraries. Then I will be getting away to Philip. So
we can skim over this.
Okay, yeah, sounds good. So would you like to go ahead and start with rendering techniques?
You can skim over it real quick.
Oh, okay, yeah, okay, so okay, sounds good. Okay, yeah, sounds good. I think this graph here could be really helpful for us to understand. As I mentioned before, UXarray supports a number of data for grid formats, including, as of today, UGrid, MPass, Icon is work in progress, ChemSE, Script, and Exodus. And as this suggests, the structure is open to extensions in the features as well. So as I mentioned before, we have grid object to understand or recognize what unstructured grid we are using. And we have our data set and data array objects here. And this is important. So for each of our objects under UXarray, we have a plotting namespace or plotting accessor that you can see individual functionalities here. So this accessor means we have a structure as simple as UX dataset dot plot dot function of interest, just like you are familiar with Xarray. So all of these functions can be called through UXarray dot grid dot plot dot mesh, for example, which Philip is going to be covering in much detail. So I wouldn't like to go that route, but that's that. And you can see here, we are wrapping HoloViz technologies for visualization purposes under the hood of this plotting library of ours. So under the hood, we are using some lower level visualization functions of HoloViz package and others like data shader. And we are just providing our end user with high level, scalable visualization functions. And also for those end users who would still like to use their own a visualization package of interest, for example, Matplotlib, we are providing some output data structures as well. For example, if you would like to use Matplotlib, instead of calling our own functions defined here, you can simply generate a Matplotlib poly collection out of our grid or line collection. Then you should be good to go. Use that data structure in your Matplotlib configuration without using any more UXarray function. Then you should be still good. So you can visualize output data structures here with any visualization library of your own preference. I think at this point, I would like to stop and leave it to Philip. Thanks so much.
Thank you, Orhan.
Sure.
All right, let's see. So now I'll cover some. Can you guys hear me fine? Okay, perfect. So I'll go over some rendering techniques to start off. So so since unstructured grids require significantly more overhead to actually represent the data and geometry that composes these grids, it's important to consider what rendering technique you use in order to obtain accurate and also good-looking plots. So the first way that you can plot data is through vector or shape geometries. So each element in an unstructured grid, whether it's your nodes, edges, or faces, they can be geometrically represented as their equivalent geometry, which I'll cover in a second. And in this example right here, we show each face shaded with a data value plotted as a vector geometry. So we can see you can't really observe any pixelation or any really artifacting in this data. So it's really high quality, but we'll see in the next notebooks, there's some pretty big drawbacks to this in terms of performance. Another example that we've already covered today is continents or different features when you're making plots. These are typically stored as vector geometries and or shapes. So here, each continent is represented behind the scenes as a shape file or some other format. And then a couple examples here using the Shapely package. We're not going to go into detail about what this package is, but it's used for representing and manipulating geometric objects. So we can see a point. This is used for representing each node in terms of its latitude and longitude coordinates. You can then pair two nodes together to get an edge, which represents the edges of our plot. And lastly, we can represent each face as a polygon, which is a counterclockwise set of nodes. And in this example right here, both the final and initial nodes, they wrap onto each other to form a closed polygon. So even though there's only 4 corners, we have 5 nodes to form a closed figure. So that's generally what the shapes and geometries would look like. Once we actually have these geometries, we can perform an operation called rasterization. What rasterization does at a high level is it takes these geometries and geometric objects and approximates them and maps them into regularly shaped bins for much faster visualizations. So this figure right here, we can see how points, lines, and polygons, they each can be mapped onto a structured grid, and or you can think of it as your image, and can be shaded that way. So here we have points, lines, and polygons. You can see in an actual example, comparing it back to our vector image, we can see plotted against the black lines here, which is the expected geometry, you can start to see the jaggedness of this plot. So while it may not be visually the best looking plot, we'll see why this option is important soon. And there's an extra link right here for some additional reading. Okay. Now I'm going to real briefly, we already looked at this figure, but just go over the plotting API and how you can work with our objects. So as we already covered, if you have a standalone grid, you can directly call a plotting method on that. And it actually looks like I need to refresh the page. So some of the plots aren't rendering, but that's fine. If we plot grid.plot.nodes, this is just an example, you can call a specific method and you have each node plotted this way. You can also if you have your data set, you can call the grid through the UXGrid accessor, and you can call the same grid specific functions. And plotting through the grid is applicable because if you're only interested in investigating and exploring the grid geometry, you don't necessarily want to map any data to these elements. You just want to explore the geometric aspect of your grid. And then through the data set and data array, let's refresh it one more time. You can call the default plotting method right here. You can also call specific ones right here. And the customization, I'll leave this for a reading after this presentation because we're running a little bit low on time. Now for the grid topology, we can plot the edges. It actually might be better if I run it through here, just so everything is rendered properly. So we can load in our data. And when we're plotting our edges, we already discussed what edges are. They're the connections between each node. You do grid.plot, which is the default plotting method, and it'll default to plotting the edges. That's one way to access it. You can also go in and plot either the mesh or dot edges. This is just an alias for the name of this method. And if we plot this here, this resulting plot looks almost the same as the previous one, but we can observe we passed through a parameter called exclude anti-meridian. With the way that we process our data, we can either choose to include or exclude the data that's mapped around the anti-meridian, and that's mostly due to performance considerations and avoiding any artifacts on the data. So here we have the mesh without any of the anti-meridian ones plotted. You can also choose a backend. So in this case, we were using Bokeh by default. Now you can choose matplotlib and have your plot formatted in the style of matplotlib using the matplotlib engine. You can also plot the nodes. So by calling grid.plot.nodes, you could, by default, it plots the corners of each face. You can also plot the center of each face if that variable is present. Otherwise, it'll internally compute it, and you can plot it that way. So that's plotting the center point of each face. And you can also plot the center point of each edge. And if we put all of these together, we can see there's the center, there's the corners, and then there's the edges that kind of put everything together. And this example here is from MPass. You can see the grid structure and where all of these coordinates are on this grid. So the next one, I went a little quickly through that one, so I had some time for this one. We're going to go over plotting polygons. So as we already mentioned, you can represent each face as a polygon geometrically. So let's load in our data. For this example, we're also going to use two data sets. One of them already has a face center data variable, which means you can just directly shade the polygon that way. And then one of them is node centered, and we'll show how you can manipulate that data to then also shade each polygon. So when we mentioned our stack of packages, we offer conversion methods for getting our data represented in a format that can be interpreted by the HoloViz stack. And that requires us to have a spatial pandas geodata frame. So you can convert a grid. So we can see here accessing the UX grid. We can convert it to a geodata frame, which contains a column of multi-polygons, which are each of our faces represented as a polygon. You can also call toGeoDataFrame on a one-dimensional data variable. So in this case, we have bottom depth, which is mapped to each face. And then we have the face mapped to whichever data variable we want to use for shading. Lastly, I mentioned we had a node-centered data set. For this one, we can take the nodal average, which is simply averaging over each of the corners to then shade the face that way. So now the first one I'll cover is vector plots. As I mentioned, they plot each geometry directly. We can see that if we zoom in, you can very clearly see how each face is defined. And this is done through the plot.polygons method for a data array. And then, as I mentioned with the node-centered variable, we can still plot them as polygons. And each of these shaded points right here is the nodal average of the node-centered variable that we have. And then for rasterization, so let me load these in real quick. We can see, instead of calling plot.polygons, you call the rasterize plotting method, which this takes in a method parameter. And to plot the polygons, you choose polygon as your method. So zooming into that same area around the Gulf of Mexico, we can see here that now we have each face approximated. So we're not plotting the shape of each geometry directly. And then going down here, same thing for the nodal average. Zooming in, we can see this approximation that's happening behind the scenes. I'm going to skip the anti-meridian section, but I'll just show off the plot real quick. So choosing to include or exclude the anti-meridian, we'll see just going around plus or minus 180. On the top one, we include the anti-meridian. On the bottom one, we excluded. So you can see there's just missing values around this point. This is for performance, which if we have time, which we probably won't, it would be in this notebook right here. Another way of visualizing this data is by shading coordinate points. So instead of actually creating these polygons, we can use, in this case, we can plot bottom depth as points, which takes the coordinate of, in this case, the face centers, and shades them according to the value of the bottom depth. So here, we can see that. You can also apply geographic projections to these. So here's an orthographic projection. There's a lot of additional customizability that's supported for these. What should we do with the time since we're running a little low? Okay, so we're going to go over a little bit, but there's still some good stuff I want to cover and showcase. So yeah, as we can see here, we have the geographic projection of a face-centered variable mapped in terms of its coordinate points. And that was the vector plot. We can also rasterize these points, which you can see it doesn't look that great. And however, this is the top one was a 400. Let me zoom out just a little bit. So this top one, these are both the same grid, but of varying resolutions. So the top one has a 480 kilometer resolution. The bottom one is 120 kilometers, so quadruple the resolution. And we can see plotting these, you can start to see the global trends of these data variables. And this is where point rasterization actually becomes a very decent method at high resolutions. So we can see here by changing the pixel ratio, which you can think of the pixel ratio as increasing or decreasing the size of the pixels that are used for rasterization. So a smaller pixel ratio under 1, you can think of it as increasing the size of how we group the pixels together for shading, and increasing it to over 1 shrinks that size. So while you may have more pixels, when you're plotting points, there may be areas where you don't have any pixels to include. So for this case of a sparse grid, there's just a lot of empty space that our rasterization doesn't know what to do with. So scrolling down, and this is a even higher resolution example right here. So this is of a 3.75 kilometer mesh with a rasterized point plot. And you can see, other than near the poles, which for a 2D plot, when you're doing this type of projection, there's a lower density of points. So you're going to be working with less points for your rasterization. You can see that the global trends, they look good, and there's really no missing values around most of the plot. And these actual missing values can be kind of avoided by choosing the correct projection. So something that roughly evenly distributes the density of points. We can see here for an orthographic projection, there's really no differences compared to what you would have with a polygon plot. So that was the point plot right there. There's also, we didn't get to covering triangular meshes, but I'll real quickly just go over visualization at scale. It's a good transition from the final one. Just a couple highlights in terms of performance. So we benchmarked our visualization methods. So we only benchmark the raster plotting because vector plots, even after about 1 million nodes, it becomes way too slow for actually plotting each geometry directly. So we have 4 data sets here, 30 kilometer, 15, 7.5, and 3.75. And we can see at the 3.75 kilometer resolution, we have almost 84 million nodes and 42 million faces, which is a really large data set. And comparing the performance for processing the data for polygon rasters at the 3.75 kilometer resolution, it took almost 2,000 seconds, which that's maybe about 30 to 40 minutes to actually process the data, which is way too long to actually wait for. And then the polygon raster is about 20 times faster, taking about 90 seconds on average, which it might be worth waiting depending on your workflow. And then the point raster took only 1 second, which is significant. Like it's a almost 90-fold increase in performance. The number of faces was about 42 million, and the nodes was 84 million. So for subsequent runs, this is also important to consider, is once you've already made one visualization, which means you've already computed and cached necessary data structures, the amount of time that it takes to then make subsequent plots, both for the polygon with and without the anti-meridian, is about the same. And the point raster, since it's already that fast, you don't need to cache anything. You can just recompute it in about a second. And just to sum up, since we are low on time, these are just the examples comparing the point and polygon plots. We can see, zooming in to the polygon raster with dynamic set to false, both the point and the polygon plots look identical. But what's important, and I want this to be kind of the main takeaway from this, is when you zoom in with dynamic for polygons, you increase your data fidelity because you can redo the rasterization and get a better looking plot. But for points, it falls apart. So you can basically zoom into a polygon plot as much as you want because each polygon covers some area of our plot. But for points, since we just represent them in terms of coordinates, after a certain point, zooming in makes the plot fall apart. So for global plots, it really doesn't matter. It actually is preferred to do point rasterization just because of how quickly you can obtain this visual. But if you have the time to wait or you're interested in zooming into regions of interest, you will want to use a polygon raster just because of the added level of data fidelity, but it's at the cost of performance. So that's, I think, everything. Any questions? Yep. Are you saying like overlaying them together or? Yeah, so that it's definitely possible. I think with the way, so most of the time is actually in the data processing aspect. So even though you can instantly process and have your points ready, you then still have to wait for maybe in parallel, you can plot one while the other one is rendering, but for the most part, these are kind of mutually exclusive. You wouldn't plot them on top of each other. You could, however, though, plot like the edges connecting the points and do it that way. So yeah, good question. Yeah. All right, if there's no other questions, I think we'll go to about a 10-minute break. You feel free to, if there's anything I rushed over a little bit too quickly, just flag me down. I can go into detail, but this is all available on the Project Pythia Unstructured Grid Visualization Cookbook. Yeah.
Thank you very much, Philip. And this is 3:13 now. And why don't we go out? Huh? Okay, yeah. And we can come back 3:25. And right before that, Nihant has a quick announcement.
Yeah, for the final part of this tutorial, we unfortunately won't be able to use Binder So you do need to download the package and run locally. So we shared the instructions in the email, but if you folks have any trouble with it, just let me know. I'll be around. Thank you.
Thank you. I had to rush quite a bit though. No, it's okay. I think it's still went okay though. I just had to skim over a couple of things.
Yeah, I think this is very, it's a short course. We could easily do the same content and do 2 full days.
Yeah. I think I covered as much as I was intending to. There was also a little hiccup of, I don't know why this keeps happening, but when you have the rendered notebook, some of the plots just don't show up sometimes. So here we can see the bottom one shows up, but if we refresh, then this one doesn't show up, but now this one does. So it's almost like there's the cached outputs of, like, they're not all rendered at the same time.
I don't know if that. I hope it's more water. Do you need anything?
It's not enough. You have your HDMI? HDMI. Oh.
Here's where.
They're setting up like a Pete's Coffee
Is that the
downstairs,
mic?
but I don't think they're up yet.
Does this go to the mic? I mean, well, it looks like an auxiliary cable. I was hoping to take this off the podium. Yeah, it does. Maybe if I just put the, can I take the Ethernet and the power and push it down there? That's it. Well, I'm just not sure if it's gonna connect. From there. Is the Zoom on this? It's on, yeah, it's on the top. Sure. Would you be able to? You should probably just put the top of there. Yeah. And the mic. I just need space for a mouse. Maybe. Good. You cold still?
I've got a nice sweater on, so it is a little bit chilly though.
I should have brought a sweater, dude. My cap business. My top street there.
I mean, that's the vibe of these conferences though.
Yeah, at least they can't see the legs at the podium.
You can see me at all.
The
I'm like as tall as Orion's laptop.
Oh yeah, I couldn't, like when I walked back in earlier, I couldn't see you past your laptop.
If you want, you can move that down.
But then I think it's gonna be too
Oh.
crowded because it's always a problem with podiums, like just
Yeah,
getting mouse real estate. You gotta have a mouse with paper.
Just set a high DPI.
I don't know. That's a good question, actually. Let's see how this comes up on the monitor. Yeah, that's good. And the-
For a long student, and then I ended up in Philly,
Yes.
San Francisco is. I like walked past my hotel. I looked up and I'm like, why is the road going at a 45-degree angle?
yeah.
Like going up it was like for a hike, but going down, it's like I was trying not to slip.
Oh, yeah, I'm glad it's not rainy this week.
Oh yeah, it's actually really nice this week.
As soon as I landed, I was like, I did not pack any rain gear. And they explicitly said to bring an umbrella.
Oh, really?
Should they?
Yeah,
It's not supposed to rain at all.
but it's not rain at all.
Fingers crossed. It's looking very pleasant. Definitely better than you were at AGU last year. So like the weather there is very Chicago's not known for
Yes.
its good weather.
So I was very happy to be in the conference hotel. So I did not have to go outside all day. So I didn't want to.
Are you guys here till Wednesday?
Here till Friday.
Saturday.
Well, Saturday morning I'm leaving like early.
Yeah, 9 a.m. Like, I haven't talked on Friday.
Oh, really cool.
So you're
I'm leaving Wednesday. Yeah.
Which one's your talk again? I think I bookmarked it.
Yeah.
I'm in the Voices from the in Science, the global community here.
This one?
No.
By any chance? I'm wondering.
Yes. Okay. So how much time should we do? 'Cause I know we're already 6 minutes behind. Or six or
I can be flexible.
15.
I have to call it off at 6:15. Okay. It's all right.
4:15.
I'm sorry, you're right.
Do you want me to just give you 30 minutes and then the rapid engagement maybe doesn't have to take?
I'll call it by
Yeah, that
ear.
shouldn't take 50.
I don't think this is a full 15.
I'll call it by ear. I've never given this talk before, so I don't know how fast or slow it's gonna go.
Would you rather I give you this block and then this block to help you face yourself, or do you want me to just set up an hour?
I say let's leave it as is, and
I think having it as an hour might be just a good reference.
Okay. And then, yeah,
give me the as it is, and then we'll ask how people feel about going a little bit further. I mean, how much time do we have?
yeah, we are just like 10 minutes behind on the back. Do you want maybe 55 minutes?
Yeah.
And then if you have to go, then if you have to go over,
Yeah. So have you guys given these talks like, in the past, or?
Technically my first like oral presentation. Like I've done posters. Well, site parts was my first, but still.
You did AGU last year?
yeah, I already talked about this. This is all the content that we just did.
Gotcha.
I just did a poster. Is the shop open?
The first time doing a Python is I think we're good though.
Okay.
We have had the idea of flipping between the two, the GUI and Python API, so we can keep on extending it.
Did you see there's a
We have to
10-minute
put all the
rapid
content
talk
for the GUI.
by Christopher Baker? It's yeah, on Wednesday. Some you definitely should.
The slide looks amazing. So
Yeah.
Oh, it's animated.
Simulation is crazy. I don't know if you've heard about it, but like, I'll touch on it. These troublesome.
Fire.
You guys, you were back in 2020, right? I thought you were always been in Chicago. No, it was started in October and ended at the end of the summer. And then I exploded almost half of it happened in one day. Yeah, I think jumped the continent side. My Estes part sort of right in November. It's weird. The same thing happened with the Marshall Fire. Yeah. It's like yeah, 2020 is nuts. Yeah,
There's probably a lot more people going to the wilderness than would, so they have the same like fire safety training and training.
Okay. Test. Can you guys hear me? Well, thank you all for coming here and sticking with it. I know these tutorials can be they require a robust attention span, so I hope I can keep it for this last portion of our talks. My name's Scott Pierce, and I'm a developer for the Vapor project at NCAR. There's 4 of us, 2 project scientists, 2 software engineers, and I really liked the dinosaur statistics example that was given at the start of the talk, because I think visualization is important. It's an important complement to statistical analysis, but it's also an important tool for public outreach and outreach to maybe not even scientists within your domain who may be administrating a grant. It's also a powerful debugging tool. Oh, is this better? I'll try to lean in. So it's also a really important debugging tool. I know many scientists who use 3D visualization to debug their codes because problems really stick out like a sore thumb when you get it into an actual renderer. So I'm here to talk about Vapor. As you can see on the screen, Vapor is an open source application, totally free to use, and it's supported on many different operating systems, including Mac OS. Hopefully soon we'll support Mac OS on the native ARM64 architecture, but you can currently run it through Rosetta. We also support Ubuntu 20 and 22, OpenSUSE, Windows, and just a note, it looks like we might be a 50-50 split between Mac OS or Linux users and Windows. Our Python API, which I'll be demonstrating, does not currently support Windows, but we're hoping that it will in about 3 months. So if you have to get to it now, you probably have to switch operating systems, and then in our release after next, we should be supporting Windows. We also support a build system for a program called SPAC. So if your operating system isn't listed here, you can use SPAC to custom compile a version of Vapor for any operating system you want. Our website is github.com, or this is our repository, github.com/ncar/vapor. And our documentation website is vapor.ucar.edu. You can email my team at vapor@ucar.edu or me directly at pierce@ucar.edu. I'll be here through, I'll be leaving on Wednesday. So if you'd like to meet up with me at the NCAR booth and work on your visualizations with your data with Vapor, shoot me an email and we can set up a time to meet up. Nihan touched on this earlier. In the world we live in, there is a whole multitude of different visualization tools in 3D to pick from, whether it's Visit, ParaView, Maya, Blender, and the list goes on. So how has Vapor carved out a user base that gets roughly 5,000 downloads a year? The way we do that is by tailoring Vapor to the geophysical science community. By listening to the geophysical science community directly and only implementing those requirements, we're able to develop a streamlined user interface that's not so bombarding towards the user. If you've ever opened up ParaView or Blender, there's just a whole plethora of options to pick from. So Vapor's user interface is what we believe has garnered our user establishment. In this tutorial, I'm going to be going through Vapor's GUI and its Python API. The GUI is what we see here up on the top left, and I'll get into more details once I open the application. We have our list of renderers. We have our visualizer that's actually giving the visualization. And then we have our area where you select your parameters that apply things like color and opacity to your data. The Python API is capable of doing everything that the GUI is programmatically. But I think Julia mentioned earlier, Python can be overwhelming. There's so many different options, and in Vapor, there are hundreds and hundreds of parameters. Finding those parameters through the Python API can be challenging. The Python API is still young, but my personal workflow is always to start with the GUI, get things how I like with my observables in a aesthetic context. And then I use the Python API to do things that are impossible to do for a human. Things like flying through the scene, something we call keyframing, which is interpolating the camera between 2 points, orbiting the scene with the camera, or even doing movement of a cross section, somewhat like an MRI through your domain. So in this tutorial, I'll be bouncing back and forth between the GUI and the API. Some of the key concepts that I'll be talking about are, number one, what is a renderer? Vapor comes packaged with 11 algorithms called renderers, which apply color and opacity to your data in different ways. We'll be touching on a few of them, and if we have time at the end, we can touch on some more of the more complex ones, depending on time. The concept of a session is the state of Vapor. You can save a session to a file and then load that session from the Python API into Vapor or vice versa. So it's a really important concept to familiarize yourself with. It just contains all the parameters that you've defined. The camera is basically more intuitive from the GUI's perspective. It's just where you're looking, and you can control where you're looking with the mouse or a trackpad. And it basically is comprised of 3 different components: a position, an up vector, and a viewing direction. And so we'll be interpolating the camera later on with the Python API. And lastly, we'll be talking about animation with Vapor through time. So with all that being said, I just want to ask if there's any questions before I actually open the application. And if there's not, is there anyone who's planning on following along? Okay, well, either way, hopefully, if you are following along, you've installed Vapor already. We're going to start with the GUI. So I'm going to click on this V on OS X. You can have, your startup icons down here. So I'll click on that. And this is the basic user interface. It's very plain right now because we haven't loaded any data yet. So there's really nothing to do. But over here on the right, we call this window the visualizer. This is where your renderers, the renderers that you instantiate will be painted to. Over here on the top left is a renderer table that shows the list of renderers you've made, and you can select on the different renderers. And when you select on a renderer, below that, the parameters that pertain to that renderer will be shown. So the first thing I always have to do is import our data. So I'll go to the File menu, go to Import, and these are the different geophysical data sets that we cater to so far. There's WRF ARW, that's the data set we'll be using today. We use NetCDF data. That is CF compliant, and CF compliant just means that your coordinate variables have a few attributes that define what your grid looks like. We also support MPAS and UGrid, the unstructured grids. We support brick of values, which is basically raw binary data. So if you have a cube of 1,000 by 1,000 by 1,000 floating point values, you can write a metadata file that describes that structure, and then Vapor can read that raw data. And then we can also do particle data when it's specified according to certain parameters in NetCDF. For this example, I'm going to be loading a series of WRF files. So this is all in the example data that I mentioned earlier. And this is sample data from the East Troublesome wildfire. If I pull this up again, the East Troublesome wildfire was a pretty unique case of wildfire in Colorado. It was the 2nd largest wildfire in Colorado history, and happened in 2020. And so this is a subset of an East Troublesome wildfire simulation that comes from WRF fire, a submodule of WRF. So now that I've loaded my data, we can see my 3D domain. We're looking down the negative z-axis, and with my mouse, left clicking will rotate the scene, Right-clicking will zoom out and in, and then the middle mouse button will traverse. You can also achieve this with the trackpad. I always recommend using a mouse though. So a single trackpad click will rotate, double mouse click or trackpad click zooms out and in, and then shift click will traverse. Up here in the upper left table, we see our imported data set. We can click on that and get metadata, such as the data set name, the kind of data that it is, and the path that it resides in. There's also a transform table down here where you can manipulate how this data set is being rendered. And typically, these atmospheric simulations are very small on the z-axis compared to x and y. Vapor by default is going to apply somewhat of a stretch factor to your z-axis. Right now, we see 2.1 roughly. I'm going to bump that up to 4 just so we can get more of a third dimension in our rendering. Now that we've done that, we can start instantiating our renderers. And I'm going to start simple by clicking on this plus button, and we can see our list of renderers. I'm going to start with the 2D data renderer, but this is just the list of the different renderers that are available in Vapor. Click OK on that. And we can see in this blue row in our render table, we have our 2D data renderer instantiated. And in our parameter area, all of the parameters that pertain to this renderer have been populated. The way that Vapor is structured is with these tabs down here. The primary tabs to be concerned with and that all renderers have are the variables tab, the appearance tab, and the geometry tab. There's also a tab for annotation, but it's not as important. Variables pertains to what you're rendering. What variables are you drawing to the screen? Appearance is how it's being rendered. How is color and opacity being applied to your renderer? And geometry is where in space are you rendering? So variables and appearance and geometry pertain to what, how, and where. To turn the renderer on, there's this eyeball icon up here. And if I click on that, the renderers are off by default because you don't know how long it's going to necessarily take depending on the size of your data. But by turning it on, we can see our default rendering with our default parameters. We're looking at the fire area, which is the burn scar of the East Troublesome wildfire. We can, so this is two-dimensional data. And one of the features that Vapor comes with is the ability to apply a height variable to two-dimensional data. So I'm going to go ahead and do that. And in WRF, HDT is usually a typical parameter that's output. So if I do that, now we can kind of see the height variable being superimposed with our two-dimensional rendering. I can now go to the appearance tab and control how the color and opacity are being applied. And that's all done through what we call the transfer function, which is kind of the beating heart of Vapor. All of the renderers are going to have some kind of transfer function associated with them that will map different colors to different data values in this histogram that we see right here. Now, this histogram is admittedly not the best example. A better example would be something like wind speed, which would distribute more on a bell curve or a modal distribution. The burn scar has a ton of values over here at 0, which we can see outside the burn area, and a few values over here at a value of 1, where we can see area that's already been burned. One thing I can do to help this is to right-click on the transfer function, and I can scale it according to a logarithm instead of a linear value on the y-axis. So if I do that, now we can see more of the values populated along our histogram. So the color is being applied to the data values on the histogram according to this color bar down here. And each one of these white dots is a control point. We have color control points and opacity control points. It's going to be hard to see because it's kind of a binary data set, but if I zoom in, you can see the white edge. And if I grab this color control point and drag it over, you can see that white edge shrink and more data values are being applied with a blue color. Same would go for the red. If I did that over here, the white would transition into red values. Opacity is with these control points up here upon the histogram. If I click on these and drag them down, those data values will become more transparent. High up on the transfer function is opaque, low on the transfer function is transparent. And so I've just masked out all these values that have already burned within the burn scar. Those are the ones I really care about though. So I'm going to crank that one back up and I'm going to turn off these other values. So now all we see is the burn scar and the transition between it and the non-burned areas. Vapor also comes with a bunch of different color maps. So to pick from the pre-bundled color maps, I can click on this gear icon. And there's all these different options. I wouldn't worry about color interpolation, but saving and loading transfer functions is something to take note of because you may want to reapply them with different data sets at different times. I'm going to load a built-in color map, and we have three different types of color maps. Divergent color maps have two different colors, which meet in the middle at white, good for modal distributions. Highlighting, I haven't used these so much, so I'm not sure what the use case is here, but we stole these color maps from CM Ocean, a Python module. So I think there are some use cases, I'm just not sure where they fall into. And then finally, sequential for sequential time series, or not time series, but data distributions. I'm going to pick on this one at the top called Black Body. And just because I've experimented with this before, I know that this is the opposite of the color map that I want. So I'm going to flip the color map around by right-clicking on the color bar and then clicking reverse color map. So now the areas that have been burnt are colored as black, and the areas that are actively burning transition into white over here. Another thing I want to do, maybe not quite yet. There's one thing I want to do first, which is give us a base map to give us a context of where we are in space. So I'll click on the plus button, and we call it the image renderer if you want to add a GeoTIFF image to the base. I'll click on the image, and I'll go ahead and enable it. And it's being drawn right on top of everything because we're not applying a height variable. So I'm going to do the same thing I did for the 2D data renderer and go to my renderers tab and click height. And now you see what's happening here is a phenomenon called Z-fighting. We're drawing two different surfaces at exactly the same points in geometry, and the graphics card doesn't know which surface to draw at which triangle. So like we stretched our data set earlier with this transform table, I can click on my 2D data renderer and go to the geometry tab. Again, this is where we're rendering, what, how, and where. I can translate this, and just because I've done this data set before, I know that about 45 meters, that's still not good enough. You're still fighting right there. Maybe go to 50. Let's go 60. Problem with this is if you go too high, then there's too much separation between the surfaces. But for demonstration purposes, I'm going to leave it at that. But I want to note our map is pretty coarse right now, and Vapor simply cannot come bundled with high resolution maps. The package will just be too big. And so if you have a high resolution simulation like what we have here, 300 meters on a side, you have to find a GeoTIFF. My favorite resource for GeoTIFFs is NASA's Worldview. And so you can find that at worldview.earthdata.nasa.gov, where you can select satellite data from numerous different satellites. In fact, the East Troublesome simulation that we're looking at right now, when it originally happened, the simulation for codes were wildly off. The fire lasted for a month and a half, but half of it burned in one day. And so first responders were in a panic trying to figure out why the simulations were so wrong. And it turns out that the fuel data was wrong. The National Forest Service doesn't have enough boots on the ground to survey the fuel sources on a consistent basis. So they were using 5-year-old fuel data. So for this simulation, NCAR scientists developed an AI algorithm that uses satellite data like what we see right here to categorize the fuel sources in real time. And after the correct fuel sources were given, the simulation had I think, 40% increase in accuracy in terms of burn area. But regardless, if you go to worldview.earthdata.nasa.gov, you can acquire GeoTIFF imagery that can be imported into data. So you would navigate to your area of interest with your satellite of interest and your date of interest, click on this camera icon, select your area, and then you'd select your resolution. There's different resolutions provided by different products. And then you would be sure to click on the GeoTIFF file format. Once that GeoTIFF file is downloaded, the geospatial information will be baked into the file. Vapor will read that, and then you can download it. If you look at the examples that we pointed to earlier, there's going to be, let's see, I'll click on my image. There's going to be a prepackaged GeoTIFF image. So let me slow down for a second. In the image renderer, you notice there's no transfer function. We're not applying color to a variable. We're just selecting an image. So our image file by default is this natural earth tiled map image that comes packaged in Vapor. We can select a different one. And if I go to the examples, AGU 2023, that would be this one right here, snapshot 2000. And here we have our base map with Grand Lake, Lake Granby, and then the East Troublesome wildfire approaching it from the west. One thing I want to do again, though, that was going to be kind of hard to see before. If I click on my 2D data renderer, I want my burn scar to be a little bit more transparent in the burned area so we can still see some of the map. So I'll click on this control point and let's see, try to turn it off and on. Maybe the image. Usually that's fixed by turning them off and on. Let me try doing this. Okay, maybe that's a bug. That should be applying transparency to the 2D renderer, but I'll just move on for now. Those are two very basic renderers in Vapor. I'm going to move on to the Python API and just show that the same things can be done programmatically. So I'll minimize Vapor, go to my console, and I don't know if we mentioned yet, there have been a couple of changes to our notebook. So if you are following along, go ahead and go to the repository for the Jupyter notebooks and do a poll that will update the notebooks to their current state. And you should see that you are up to date. And from there, Jupyter notebook. Probably have to zoom in quite a bit. So the example I'll be going through first is called AGU 23 example.notebook. Okay, and so the first thing we have to do is set our home directory to the location of the sample data. So for me, that's in users, Pierce, downloads, AGU 2023. And here's a link at the top for the sample data in the notebook if you want to do this later on at your own pace. So I'll go ahead and set my home directory so we can reference the data and write files to that location later on. And then the first thing we're going to do is create a new session object. So from the Vapor module, once everything is installed, there's this session object that's going to control again, the global state of Vapor, all the renderers, all the parameters, everything gets saved into the session object. This is how you can go from one application like the GUI to the Python API and then restore your sessions at a later time. And then we're going to instantiate it by calling the constructor on the session class. So like Julia was saying, it's easy to get overwhelmed in Python. There's just so many options. So the first thing we're going to do is find documentation on different objects that we'll be using as we go forward. So we're just going to call help like we do with any other Python object on our session class. And here's how you would do it for a renderer, a camera object, and an animation object. And alternatively, you can look at all the documentation at our website at this link right here, which lists out all of the different functions. And you can see it's a lot. So this is why I like to start with the GUI, find out what I want to change in an animation, and then find that parameter that I want to change in an animation, and then find this function and then write a script around that. But you can also get your help context here, where all the functions are basically spelled out piecemeal. In the renderer, probably the important ones to look for are open dataset, where you point to your files and the dataset type, and then instantiating renderers, I think, with this new renderer function, and then going from there. So now that we have a session, the basis of everything we're doing, we're going to load data into it. I'm going to cheat a little bit and use the path module so we can glob the directory where my data exists. So all my files will be stored in a list that we see here. I'm going to print those files out just to be sane, make sure I'm importing the right things. And then I'm going to import the dataset object. And then my data object will be a call upon session to open the dataset. We will define the dataset type. In this case, it's WRF. And finally, give it the list of our files. So there's the files we've incorporated. And then we can look at dataset metadata. Did that not run? Oh, it's okay, so we'll show the coordinate variable metadata first. And this will just be calls upon our new data set, get the time coordinate variable name and get coordinate variable names. And there's that, which I forgot to mention can be done in Vapor. If we click on our data set, there's also a metadata tab that gives all the data about coordinates and the different variables. The different variables can be interrogated with these functions. And here we see our data variables like fire area for the burn scar, the height variable we were using to offset pH, PHB, perturbation, UV and W, and then finally fire smoke, which is one we'll get to in the GUI with the volume renderer in a bit. So now we are going to create a 2D data renderer just like what we did in the GUI. So from Vapor, we import this renderer class, which contains the whole superset of the different renderers like the image renderer, 2D data renderer, and many others. So to do that, we call new renderer upon data and just specify the 2D data renderer is the one that we want. And then we're going to set the variable name to fire area for the burn scar. Now that the data has, or the renderer has been instantiated, we can now show it finally. And here we are at our default view of our 2D data renderer looking down at the negative z-axis. Let's again apply the height variable so we can get that mountainous terrain. And looking down at the negative z-axis, we really can't see any mountainous terrain. It's pretty flat. You can barely see some contours over here at the top right. So what we need to do next is make this interactive. So to do that, Vapor comes with a module called Jupyter Vapor Widget. We're going to import everything from there, and amongst everything that's being imported is the Vapor Visualizer widget, which allows you to have a visualizer in a Jupyter notebook, kind of like we were using in the application. So I'll click that, and then the visualizer is just an object we can call viz, and just like any other Python object, if you want to print it, you can just type its name there, and then it will come out onto the screen. And so now we can click on this and rotate it in the same manner that we were doing with Vapor a moment before. We move on to the transfer function because we still have to apply color and opacity. We have to import this module called utils, which has a function called show a matplotlib histogram that shows the transfer function that's being applied. So I'll go ahead and run that. And here's our big impulse at the value of 1, or the value of 0, a smaller impulse at the value of 1. We can apply opacity by specifying specific values at the data value and the opacity level by first acquiring the histogram that's associated with our renderer and our session. We then apply opacity values. So at the data value of 0.2, I'm going to have 0 opacity, so that will be completely transparent at a value of 0. At a value of 0.8, we'll have a maximum opacity of 1. So we'll have a ramp going from 0 to 1 between the values 0.2 and 0.8. And then we can plot that as such. If we re-render this, we should be seeing no values outside the burn scar and only values within the burn scar. So again, we just set the opacity control points to what we did earlier and recall viz. So we get another visualizer. Let's see, make this a little bit bigger. And then we can see that the areas outside the burn scar have been masked out in the same way that we did in the GUI. And we can also load built-in transfer functions by just passing in the name of the transfer function, this one being sequential and black body. You can also load pre-generated transfer functions like what I was alluding to earlier with loading and saving transfer functions in the GUI. Doing that through Python is just calling the load color map from file function upon the transfer function, and then pointing to the file which is included in the sample data that was distributed. After that, again, we call viz.render and then display the visualizer. And here we have our burn scar according to the transfer function that we had from the GUI. So those are the basics. I wanted to show that everything that can be done in the GUI can also be done in the Python API. There's another component I want to move on to, but I want to give the opportunity for any questions before we jump to this other notebook. Yeah. Yeah, that's like on the docket right now. What we are thinking about doing is having, because right, you have to find the right function call, and the label will give you a hint, but what I believe we need to do is have a tooltip show up. So when you hover over, let's see, most of our items have tooltips. But we need to give the exact function call and the parameter so that you have a one-to-one mapping between the two. But that's a great question, something we're actively looking into fixing. Right, so just to give you a quick peek at what that looks like, et0.vs3. This is a session file that I've saved for the demo, and it's just an XML file. And let's see if I look for tag. All of our parameters are suffixed with the word tag. So, for example, the moving domain track camera tag, you can find that there. However, that's still not going to give you the function that you're looking for. You can call and manipulate individual tags programmatically, but I think you're looking for more of a function call, which is easier to use. So that's like another component that we'll have to add in, as well as the tag that a parameter is affecting. Did I see another hand? Yes. Yeah, you can capture still images or animations, MPEGs, and that kind of thing. And so that's coming up at the tail end of the talk. Any others? Okay, let's jump into this next part because it's kind of cool. So these are more interactive components that you can find in the Python API. Let's see, I'll go to my directory over here. And this next example is called the visualizer widget example. I'll open that and let's see if I can restart my kernel. Looks like I'm good. So what we're going to do here is we're going to add widgets like sliders and stuff to our visualizer so we can change them in real time and make our own custom GUI. That's like Vapor, but much more simple if there's only a few things you want to adjust interactively in a notebook. So let's see. Go ahead and kick this off. And we're going to be using the example data set. This is going to be adjusting an ISO surface, which for performance reasons wouldn't be a good example. It would take too long. It's not that interactive with the data set we were looking at earlier. So again, I will create a new session. And after importing these different modules like session, renderer, data set, and the camera, so we can do various things, I'll move forward. Now I'll render an ISO surface. So again, we create a new renderer called the volume ISO renderer. And that's kind of a legacy name, not legacy, but it's because our volume renderer and ISO surface renderer are highly coupled. So our volume renderer is called the volume renderer, but the next iteration on that is the volume ISO renderer. We're going to set the data variable name for our ISO surface to the first three-dimensional variable in our data set. And then we are going to just budge the ISO value up by 0.1. And if you're not familiar with what an ISO surface is, it's a three-dimensional contour. It's just a surface where every single data point along that surface is the same data value. And we'll just simply show the session. Again, this is not a visualizer, so it's a still image. And I think the next step was to create an interactive visualizer to explore the scene. So this is what we did before with the Vapor Visualizer widget. And now we can rotate. And finally, we can add the interactive ISO value slider using IPy widgets. So basically, what we need to do first is, well, what happens first in this cell is we get the primary transfer function and we get the minimum and maximum values of the transfer function so that we have 2 points to start and end from our slider, a minimum and a maximum value. We'll call that array data range. The next thing we need to do is a callback called slider change. When we make our slider, it's going to be watching for changes to itself and then issuing calls to this callback whenever it senses that a value has been changed. The result of this function will be to set the ISO values of our renderer. Our ISO surface renderer can support, I think, up to 16 different ISO values. So you can have 16 ISO surfaces in a single renderer. Right now, we just have one, and that's by far the simplest use case to go with. So we're just going to take this change value that was passed into the callback and apply it in a one value array, and then call render upon the visualizer. Lastly, we instantiate our slider through the widgets module. We have a float slider class. We also have integer sliders, double sliders, and all sorts of checkboxes and that kind of thing within the widgets module. The values that it takes are first the initial value, which we're going to go with the default value, which we budged, I think, by 0.1 earlier. And we're going to give it a range. The minimum and the maximum are just going to be the first value of the data range and the second value of the data range. And then we give it a step size, which will be the difference of the data range divided by 100. We will have 100 steps to scroll this slider upon. Finally, we pass the callback into our slider with the observe function. And then we create a VBox. So this widgets module has this concept of vertical boxes and horizontal boxes. What we're doing here is we're creating a vertical box that's going to contain two things. At the top, it will contain the visualizer. At the bottom, it will contain another horizontal box, which will contain two components, a label and the actual slider. So up top, we have the visualizer, then we have a label, and then a slider beneath that. Once we execute that, and I think, let's see if I can zoom out a little bit. So we can see our visualizer up here at the top, our label below, and then the slider, which should be interactively, that looks like could be a bug. Should be one isosurface. Well, we'll have to look into that, I guess, after the talk, but I think it gets the point across. You can create your own GUI that's interactive in a Jupyter notebook for highly reproducible cases in your data. So I think after that, I wanted to get back to Vapor just to demonstrate one of our flagship renderers, the DVR. So I'll bounce back over here. And I'm going to, despite the fact that the opacity is not being drawn correctly here, I'm just going to create a new volume renderer by clicking on the plus button and clicking on volume. Okay, now let's see, I'll go to my variables tab for what I'm rendering. I'm going to pick the fire smoke variable to get the smoke field. Go to my appearance tab. And I actually have a pre-made transfer function that I'm going to load into here by clicking the gear icon, load transfer function, and then smoke.tf3. TF3 is the file extension for a transfer function in Vapor. I'll open that and then go ahead and enable it. And then, after some playing around, that's that bug. So on the M1 processor, which I'm using right now, Apple will issue a timeout on certain renderings. I hyperslabbed this data to hopefully avoid that. But let's see if I open, so I saved this session earlier. I'm going to open it and recover from where I left off. But one of the things about the Python API is that it's more resilient to those kind of errors. And so I'm going to do my renderings in the actual Python API. Let's see, I'll load East Troublesome 1. And here's where I was hoping to have left off a second ago. I won't play with it too much to try to avoid that timeout error. But the next thing I'm going to do is use the Python API. I mentioned earlier, you can do things that are impossible for a human to do with the API. For example, if I wanted to do this keyframing technique where you kind of fly the camera through a scene, I would have to manually use my mouse and budget over and over, and it's just not tenable. So what I'm going to do is I have this session file saved. I'm going to save another session file from a different perspective. So to save the session file, I go to File, Save Session. Oh, Save Session as is. ET1. Here, I meant to save that one as a different name. So I'm going to go and save this back as ET1 from here. And then go to a different perspective. File, Save Session as. Call this one ET2. And I'll go ahead and replace it. Ooh, that bug. Well, that's okay, because now we're going to move over to the Python API, which doesn't just close the application. It's just going to render. If it fails to render, that will be that. And it will move on to the next rendering. So to do a time series animation, we're going to first load that ET1 session file. And we're going to render all 8 time steps in the animation that we loaded, or in the data set that we loaded. So I'm going to create a new animation object and get the number of time steps so that I can loop through them. So for each time step in the range between 0 and the number of time steps. In my session, I'm going to adjust the time step. I'm going to capture the frame in the animation class, and then I'm going to show an interactive animation of that. So you can see that, let's see, I timed it up here at the top. And if we look at the timing of it, this is one of the other cool things about the Python API. It's much faster. I'm not sure why it's faster than the GUI, but I have to zoom out. Let's see. Yeah, so the wall time was about 22 seconds, and I think it's about a factor of 3 higher in the actual GUI application. And so whenever I do renderings of time series, I'm always saving a session file in the GUI and then capturing them through the API. You can look at them interactively like we just configured by pressing play, and I think this is going to go at a reasonable speed. There's this animation interval controller down here, so you can adjust how fast it's playing depending on that. I think that's frames per second, so that is instantaneous if I go to 1,000, but if I go to 30, that's still pretty quick too, but that's how you can adjust that kind of thing. You can also go into loop mode, I believe. Yeah, still a little fast, but kind of gets the idea across. So now we're going to keyframe. Earlier, I saved 2 session files from different perspectives. We're just going to do a linear interpolation upon the camera in each of those sessions. So the first thing I'm going to do is import my session and camera modules. I think they're already loaded, but it should be a no-op. So we create session 1 by instantiating a base session. And then we load the session, or the session file associated with the first camera position. And then from there, I mentioned the 3 components to a camera: the position, the viewing direction, and then the up vector. Those 3 things define where we're looking. We are going to pull those values from the, first we will grab the camera from that session and acquire a direction, a position, and an up vector, each of these being triplets corresponding to X, Y, and Z. We do the exact same thing for the second session. And now from here, we just calculate the delta upon which these 3 components have changed between the 2 session files. So the delta of the position on the X, on the Y, and the position on the Z axis are stored as those variables. The direction, same thing. And then the up vector on all 3 axes. It's just how much they've changed from one point to the other. And then over the course of 50 time steps, we're going to just interpolate new values for the X, Y, and Z components of those values and then apply them to the camera. So camera 1 will now have a new position that is an increment of the current value in the current range. And so we were asked earlier, how do we save these files? One way to do it is to call this render function, where we can specify a literal file to write to. See if I could zoom in a little bit on that. So right now I'm just saving each one of my 50 time steps as a PNG file. So if I go to my Finder, and let's see, I think I navigate to AGU 2023, and I put it in captures. I can select all of these. Oops. Meant to open. Let's do that again. And then, it's not going to be high resolution, but here we can see the camera being interpolated between the 2 points from those 2 session files that we saved earlier. The next thing I'm going to do, see, PNG. Well, I'm not sure. I'll investigate this error later, but I did the right thing. So I'll move on to orbiting, which is another camera tool that we can use. And I do want to mention, one of the next things that we're trying to do is incorporating a set of utility functions in Vapor so that you won't need to use this kind of script. We're hoping to bake it into the API so that you can just pass it two session files and maybe a number of steps to interpolate from. So you can just do a one-line function call instead of relying on this. But for the time being, this technique is here in the notebook for you guys to use, as well as this other one, this camera orbit technique. So for this one, we're just going to revolve around the scene. I think I had a slide at the very beginning that showed a hurricane that we were just spinning around along the z-axis. This is going to use several different linear algebra functions from NumPy as well as SciPy. So those are not included. I believe NumPy is, but I think SciPy is not included in Vapor's distribution. So it's an extra module you will have to load, at least for the Python API. And then here are some of the parameters. We, of course, pointed to the session that we want to load. We are going to make an MP4. So this is another way that you can save your files to an actual MPEG instead of having to post-process a bunch of images like we would have had to have done in the last example. And we're defining things like the frame rate, the video resolution, the dataset time step frame rate. So if you wanted to animate through time series, you could control that here. The number of seconds, the rotation speed, and the rotation axis. I think it's always going to be your Z positive axis. Otherwise, it might make you feel sick. So I think those are the major components. And then we're basically going to load the session, specify those components, and then load the camera parameters, position, direction, up, and the target. And then specify this rotation matrix. I think this is the exponent of the matrix, just doing linear algebra on the scene so that we are just nudging the camera incrementally across the point of origin. And finally, we're going to create a new animation object. And then for each time step or each increment in the range, we're basically going to apply that rotation matrix. This is a no-op right here because we're keeping the single time step. But we're going to apply that rotation matrix and then set the camera according to the position, direction, and up value that the exponential matrix operation did to our positions and etc. We're going to capture the frame and then render it and then finally save it to an MPEG. You could imagine how long this would take in the GUI, if this was even possible in the GUI. This would probably take an order three times as long to process. So it's much faster with the API. And here we have our saved file, which we can open by clicking on it. And it should give us a pop-up. And there we go. Kind of stuff is just not possible to do through the GUI or through human controls. So I have a little bit of time left. A couple of things I want to touch on, I guess, in the GUI related to Python is that in the GUI, you can derive new variables using a baked-in Python engine. Vapor comes with its own version of Python that you can use to create new variables that may not have existed in your data set. So what I'm going to do is I'm going to, let's see, I'll open one of my pre-cooked sessions. And that's interesting. That hasn't happened up until now. I think it's the volume renderer that is causing this this timeout on the graphics processor. Can I reduce the visualizer size and then open the session and then turn it off? Okay, turn off. Good. Okay, so now we have our session with just a base map and a 2D data renderer. I am going to make a barb renderer, I think, because a good derived variable people typically look for is wind speed based on the UV and W components of their data. So the first thing I will do is go to my tools menu and click on Python variables, which is where we'll derive our new one. Click on new, and I'll give my script a name, speed. And I have to pick the input variables to the script. So you can pick 2D variables or you can pick 3D variables. Of course, I pick U, V, and W for wind speed. I have to create a new variable. And so one of the things I have to do is pick the output grid. If you guys are familiar with WRF, the Arakawa C grid is staggered, and U, V, and W are not on the same grids. We have to unstagger them onto a cell-centered grid. So my output variable is going to be west, east, south, north, bottom, top. My variable name will be speed. And then I will use, Vapor also comes with some utilities that are useful for this kind of thing. So stuff that we want to incorporate into the API moving into the future, just convenience functions. So from this module that comes with Vapor utils, import everything, and then I'm going to create some unstaggered variables. UU will be U unstaggered, and that will be equal to the Vapor utils function output staggered to unstaggered grid. And then my input variable will be U, and the axis upon which it's staggered is 2, because the ordering is backwards from C style. Unstaggered V will be the same thing, roughly, except on that index and based off of the V variable. And then I might as well just copy and paste that whole thing again. W. And then finally, there's another convenience function called mag, short for magnitude. Speed will be equal to mag, UU, VV, WW. We can give that a test. It failed. Let's see. Show details. VV not defined. That's because I did not rename the variable VV, or I input the wrong variable. Should be UV and UW. UW. Okay, there we go. Okay, test passed. I now have a speed variable that's derived off of my inputs. This is going to take longer to render because we're reading 3 variables to perform a rendering instead of 1. But I can apply this to something like a barb renderer. So if I create that, press the plus button, double click on wind barbs, the first one in the list. By default, the barb is going to pick your UV and W variables. And then below these, we have a color map variable. From that, I can pick my speed component. And simply turn that on. And we have our basic rendering of barbs, but I think the color map is not spread out in an effective way. So again, I'll go to the Appearance tab, how we're rendering, and then constrain it so that the ends are more saturated in their color. And then if we want to go crazy, we can, first I will reduce the length scale, make them smaller, and I will increase the number of barbs in the scene. And I can just max it out just to show you guys kind of what that looks like. And if we animate this in time, we'll kind of see something like what we saw in the introduction of this tutorial, where we have the wind barbs moving with the wind colored by speed according to a certain prescribed color map. So, Orhan, did you 3 minutes? Okay, I think that's enough time to give you a cursory glimpse of the flow renderer. It's another one of Vapor's flagship renderers, but it's also the most complex one. But basically, it lets you, let's see, I think I have an animation up. Let's see, because I guess picture's worth 1,000 words kind of thing. No. World view here. So the flow renderer allows you to do 2 types of flow. There are streamlines, which are time invariant. You basically draw a line along the vector field that you're tracking at a single time step. And so that's a streamline. There's also path lines, which are time variant. It's as if you were just throwing a bunch of feathers into a wind field and seeing where they would advect through time. So that's kind of what we're seeing here with an ocean simulation. So in Vapor, of course, as you always do, to create a new renderer, you press on the plus icon and then double click Flow. And by default, you can see there's more tabs with the Flow renderer because it requires them because it's more complicated. Go to the Variables tab. Vapor with vector field renderers will always pick UV and W as the default variables. You can also do two-dimensional flow as well as 3D, and that also applies to barbs. But we don't have any 2D UV and W values in this data set, so I'll stick to 3D. The Appearance tab is super important in the flow renderer, but there's this new tab called Seeding, which defines where you are putting your seed injection points, what kind of flow you're doing. You can see by default we're doing streamlines, but you can also do path lines. Path lines are more computationally expensive and more complex, so I'm going to stick to streamlines for now. You can pick the whole litany of different options, whether you want to advect them forwards or backwards in time, periodicity upon the edges of your domain. But let's see. By default, we just do a gridded distribution of seeds, and let's just turn it on to see what it looks like. So what we can see here is we are distributing a 5 by 5 by 1 grid of streamlines within our domain. They all start at the dead center of this red box. I can increase them. Let's see, that didn't take too long. So if I go up to 20, you can see I just increased the number of seeds along the x-axis to 20. And I can do the same thing for the y. And you typically want to do axis-aligned streamlines, I think. If I do too many on the z-axis, things get too occluded, and you can't see what's going on. There's other options like random distributions and random distributions with bias. So you can have a bias variable. Say you only want to look at streamlines in areas of high wind speed. So I'm just going to, well, let's see. If I just do random with bias, seed count of 50, I'm going to pick my speed variable and then crank up my bias weight so that I'm looking at flows that originate from points with very high speed. All of my streamlines are going to be allocated to the highest wind areas, which you can see makes sense right over the Continental Divide during the windstorm. So cranking it all the way up to 10,000 is probably not what you want. You can turn it down and, well, turn it down more. And they should be distributed. Well, now we have negative distribution, so now we're looking at areas of lower wind speed. But it's something to fine tune if that's what you're looking for. The rake region, I touched on geometry earlier, where we are rendering in space. The rake region is like, actually, I didn't think I touched on that. The rake region, you can, let's see, if I turn off flow and I do my barbs, I can reduce the extent of where I'm rendering to in space by clicking on these sliders interactively in the visualizer or the sliders in the control bar. I'm still on the flow. So if I go back to my barb renderer and try that again. So now I'm only loading the data in this volume onto my graphics card. So if you're strapped for graphics memory, this is a way not only to consolidate your rendering into an area of interest, but also to save on graphics memory. But what I was talking about before was the rake. The rake is a similar principle. It's just where you're putting your seeds, your path lines or your streamlines within the volume. So here are the controls for that, the rake region, the rake center. You can also write your flow lines to a file. So if you're interested about what the data values are along a flow line, you can kind of interrogate. Like if I was curious, let's see if I turn my flow renderer back on, and for sanity reasons, let's just do one streamline, gridded, one streamline at the middle of my rake. We have this guy right here to come down. And I wanted to know what the values of the smoke field were along this certain sampling rate along this streamline. We can write those to files and do statistical analysis on those later. Couple of appearance features are we can increase the radius scalar, make them bigger, apply 3D geometry, and 3D geometry kind of skews the color mapping. So take that as you will. It's more of a qualitative than a quantitative tool, I would say things become at this point. You can render samples. And then there's this interesting algorithm that, well, I can't get into right now, I'm out of time. But as I said earlier, there are hundreds upon hundreds of parameters in this application. Exploring them through the GUI first is what I recommend, but maybe there's approaches that I haven't discovered yet. But then taking single parameters into the Python API, changing them there and doing things that you couldn't in the GUI are the current workflow as it stands. Thank you.
Okay. So this wraps up the end of today's event, and we know it was too much material. Any questions? And in the meantime, let me just present the final slide of our event today. So as far as we know, AGU asks for some input of yours. So let me just start this one. And if you can scan this QR code, I think there are going to be a lot of questions about how impactful this slide event today was. So you can definitely do that. And also, if there's any questions immediately now, we would like to answer them as well. Yeah, please go ahead. Do we have any microphone, by the way? Oh, okay. Okay, yeah. Okay. So Scott, Nihant,
It sounds like you're a ParaView user that's trying to transition to Vapor, but I didn't catch the hard part that you were facing. For Windows, yeah, we've supported Windows as long as I can remember, but not the Python API. The API is coming up, fingers crossed, in 3 months for Windows. Yeah, you can shoot me an email or shoot my team an email. I'm Pierce, P-E-A-R-S-E at UCAR, so cool, yeah.
Yeah, and actually that's a good feedback that we've gotten, that if you're not able to find the Windows installer, then yeah, that's something that we could improve. So if you have any feedback, it's a work in, like, we are constantly developing. So please feel free to contact us at any time. We really appreciate that.
Thank you. And for your question, you can also, I think, reach out to Nihant through this email, right, Nihant? And yeah, so this is my email, and this is Nihant's. So GeoCAT or Vapor related anything, just reach out to us. Any more questions? We have maybe another like 3 minutes.
Thank you all for attending.
Yeah, thank you very much for joining us today. Okay, so it looks like we can honor 3 minutes of ours. So thank you everyone for joining us today, and have a good night.